happy new year to you. So in this video, I'm going to be building a Rust game using the Bevy engine. So I'm going to be telling you more about Bevy and what we aim to do. So actually, let me say this is just a build along whereby you learn how to use Rust to build and also to learn some Rust concepts, right? Because you want to learn by building, and that's basically the idea of this session. So yeah, it's easy for anybody to pick up, whether you're a beginner or an intermediate developer. This should be easy for you to work with. It shouldn't be crazy to understand or work with. So the idea of this video is just to show you or to teach you about Rust, why you doing it, building something significant. And in this case, it's going to be a game. So even if you are starting Rust today, this is a very good place to learn because I'm going to be explaining it like a novice, basically. So that is going to make sense. So whether you understand Rust as a beginner or an intermediate developer, it doesn't really matter. You still learn from this. And if you're an expert, well, this is not the video for you, but you can still learn something because it's still fun along the way. So yeah, basically that's the intro for this video. So let's jump right into it because I want us to cover a lot more things today before we wrap up for this session. So I'm going to call this a part one session because I'm going to pick up another session tomorrow, which is going to be the part two because you can't fully understand everything we are going to talk about today in just one session or one go because it will be a lot of information and then can lead to noise. But like I said, enough talking. Let me keep building and then we'll talk along the way. It's easier that way for you to understand. So but basically this is what I'm trying to do and this is what I want us to learn together. So yes, welcome to this video series. This is going to be a series of building certain things. It's going to be a big series of building different things using Rust. So you are going to learn about Rust and other programming languages. So generally, this channel is about teaching you programming by building stuff. So we don't just show you and just give you theory. We build it here. You see the mistakes I make. I make also, then you learn from it, and then you also do stuff from there. So yeah, I think that's enough intro. So let's get into it. So today, like I said, I'm going to be working with Bevy. Let me increase this to give enough room space. So we are going to be working with Bevy today. So what is Bevy? Bevy is a Rust game engine. Let's just leave it at that. There are other things to know about Bevy, but basically it's a game engine. So you can see a refreshingly simple data-driven game engine built in Rust, free and open source. So it's also open source. So if you're interested, you can learn more about it, go to the repo, understand what's happening there. And if you are new to this, it's going to be just be picking it up today and building, basically building. So we are not doing anything crazy. We are not doing anything that you can't pick up at your own pace as well. So yes, time to continue this. So this is Bevy. Bevy is a game engine that basically uses the ECS system. So ECS system, let me use this. So we talk about the ECS system. So Bevy is a game engine built in Rust, right? Uses the ECS system, or let me say using the ECS, should I call it now? Uses ECS basically. Uses ECS. So ECS in this case means entity, component, and systems. So entity in this case are like the objects, or let me say living things, non living things that you tend to interact with within the game. So when I say living things, I don't mean they are alive, right? But like humans in your game are more like entities. The cars are entities. The trees, they are entities. And that you can look at it from that perspective. So anything that you can interpret as something that should be alive, even though it's not alive or in the game, you can think of it as an entity. Basically, entities are just objects that you personalize, right? Those are entities. So components are more like the should I call it the modules, the modules, or let me say the instructions. Basically, they are just logics that you give to your entities that you can reuse across the game. And then systems are just general to your whole logic and flow of the entire game. Now, I don't want to like go into details. That's why I'm trying to just use a word that seems abstract, but that can give you a high level overview and understanding of what Bevy is. That's basically what I'm trying to do here. So let's go back to the tutorial, you say Bevy is already a game engine. It is data driven. Yeah, I forgot to mention that. So it's data driven. Simply means that all the engine and game logic uses the ECS. Exactly. That's what I was explaining here. It's a custom entity component system. So basically, you have the component. You can see you derive the component. It's not like you defining instructions for that particular entity. In this case, now your player is your entity. The component is more like the instructions you want to pass into it, the macros, the instructions, the flow, the reusables, all of those things. And then your system is where you encapsulate the entire logic. Your system becomes like the world that you interact with, basically. Just on the high level, understand it. When we start building it, will make more sense. I don't want to go into details, so just understand it for now. Yeah, and then we'll proceed from there. So Bevy is basically data driven. We already understand that. So it is fast because, of course, it is built on Rust um, parallelism. So it makes a lot of sense to build a game engine that is fast, actually. So, and it is cache friendly. That is very important because it's parallel, massively parallel, parallelism, like I said, and it's based on cache. It is simple to understand because the components are just struct. The systems are Rust functions, basically. The entities in this case, which is this, that you can define as a player, are just component. They are just struct, right? And then your systems are function that you can see from here. So the capabilities, you have queries, you have global resources, you have local resources, change detection, lock free parallel scheduler. You have all of those things that makes a game, right? Scheduler, right? The real timeness, the untimeness, the whole scheduling system, the global resources, all of those things. So you have everything also in Bevy. And also has this 2D renderer, 3D renderer. So you can actually build 2D games, 3D games, basically anything that requires FE computation, even if it's not game simulations, whatever, you can build that using Bevy. And it's actually very simple, right? So it has a render graph also where you have custom render pipelines. You can compose them using a graph structure, parallel still, modular, and then is agnostic to backend, doesn't really tie to any specific API. So you have the animations. Yes, Bevy is capable of animations too. It's actually very interesting to see. It has a capable animation system, a skeletal rig driven by the same ECS based joint API. It has that, and it's cross-platform. So whatever platform you're using, whether you are using a Mac right now or you're using Windows or Linux, it works perfectly on any platform. But for this particular video, for me, I'm going to be using Mac OS because I use a Mac. So I'm going to be installing Bevy on the Mac, and then I'm going to be using that. But if you're using Windows or Linux, it still works perfectly. You don't even need to bother yourself. Just install. The instructions to installing is there. So we are going to be doing that also. So that's basically how we are going to be working with today. So installation, then we'll try out some examples. We learn from there. I explain how Rust can. So like I said, even if you're a beginner, right, this will work for you. You don't need to bother about, oh, I don't know anything about Rust. It's beginner friendly. Like literally, I'm going to be making sure. Take it as if I'm also learning it today. That's basically I'm going to be teaching it. So when I say some things that makes no sense, if you already understand Rust, just try to understand that we are making sure it works for everybody here. So that's basically what we are trying to achieve today. So yes, let's jump into it. We've spent how many minutes? Let's see, about 6 to 8 minutes, 8 minutes thereabout. All right. So first things first. So another thing they are saying is their sounds auto reloading. Yeah, auto reloading is very important because you do not need to actually recompile your code, right, to get results. So there's auto reloading, meaning you get instant feedback when you make changes in your app without needing to restart or recompile the program. So that saves you a lot of time when you're developing. And compile time also is quite fast, right? It makes a lot of sense, and it's free and open source. Very interesting insight. So yes, let's jump into it. So we've already learned what Bevy is. You can see come back to take a look at this and read a lot of more information about it. So, but basically, let's jump into it and try to understand. First thing we're going to be doing is we're going to be installing Bevy. So for me, I already have Bevy installed, right? But let me just show you how to do that here. So let's see if this is big enough. I think this should be big enough to, yeah, this should be big enough. So this is Bevy, right? And introduction, Bevy is a group of words. You can read all of this later on. And yeah, Bevy is still in the early stages, so it's not something you want to go into production with. And that's why I said if you're an expert, this is not probably what you want to look into for production type of things, but you can also contribute as an expert to the library so that it gets more stable quickly, right? Because it does prospect. Bevy is a very prospective library or framework. Let me call it framework. That's you can actually, as a Rust developer, build very significant games. Like you are going to see, I'm going to show you examples of games that exist, and we're going to be using the examples to also create other games by tweaking it, seeing it in action, and that should give you confidence working with Rust, right? So that's basically what we're doing today, and that is our focus today. Like that's it. So yes, it's very new, and from the Rust documentation itself, if you are currently picking an engine for your next big project, it's recommended to use Godot that you can script it Rust. So that should be put out there. So let's move on. So let's go to the get started page where you can install this. So you can try the examples here by cloning the repo, but we're not going to do that. We're going to be doing it ourselves, not just cloning and running it. We need to actually type, make errors, see the changes to build the confidence. So that's what we are going to be doing today. And we are going to add Bevy. You can add Bevy as a dependency to whatever you're doing. So basically that means you can clone the examples directly or not. But in this case, we're not going to be doing that. So we are going to set it up. Currently, like I said, I have it set up already, right? So yes, if you're itching to start making games, let's proceed. So basically, we are going to start by installing it. Currently, like I said, I use a Mac OS, so I already have this installed. And if you're using Windows, this is instruction. You need Visual C++ build to install that. For most people that have like very large applications, you must have installed this already. It's required before you install some certain applications. So definitely, I'm sure you have this installed if you work with Rust. So Linux also, you just follow it, the instruction as Linux dependencies, and that you can just use it from there. So I already have it installed, and so yeah, basically I have Bevy installed already. So let's see. I think I have this here. So I'm just going to increase this. I'm going to increase the size to give more room here. So I'm using WAP. WAP, this is basically WAP. It's my terminal when I want to do some crazy stuff. Okay, I don't have that installed. So yeah, basically, let's see. All right, let's proceed. I wanted to check. There's no point checking it now. Let's proceed with this. So, like I said, I already have this installed. You install this, right? To installing the dependencies, you start with the OS dependencies first. So once you are done with this, you want to now start creating a new Bevy project. So what you need to do is after installing Rust, I assume everybody that is here have Rust installed. But if you do not have Rust installed, then basically you can install Rust by getting started from here, and then you're good to go. And one more thing, for the Bevy itself, right? Like I said, if you want to do that from here, all you need to do is just install Rust and then add Bevy as a dependency. So I already have all of this set up for, like all this setup are already done for me. Basically, I have VS Code installed. For Windows, you need to have this, like I said, and for Linux, you follow this. So all you need to do to add Bevy is not to install any separate package. It's just to install it as a dependency in your project. You install cargo, add Bevy, and basically you are done. So now let's get started by creating a Bevy project. So I'm going to be using Rust Rover for my own as an IDE, as my IDE. So I prefer using Rust Rover. Rust Rover is an IDE from JetBrains. Basically, is I prefer it because it's useful for me. Let me just use that word. So you are free to use anyone. You are free to use Cursor, you're free to use Kilo Code, you're free to use VS Code, you're free to use any other IDE you prefer. But personally, I prefer using Rust Rover. It just works for me. So I'm going to be starting with this, and I'm going to create a new project, right? Because basically I'm working with a new project here. So I'm creating a new Rust executable project. So I'm going to create a new project. I'm going to just create a new Rust project, Rust. And like I said, you can use any other any IDE of your choice. There's no restriction to any IDE you want to use. So it's just a choice. For me, I prefer using this. So I want to customize the size of my IDE. I want to increase it to make it easy for you guys. Yeah, 20 is a good is a good one. So I'm going to be using this, and going to the project, I will select a new project. Just going to call it Bevy 101. Basically, I think I have a Bevy 101. I'm not sure, but then we'll check that I have a Bevy 101. I'm going to create as a binary application because that's basically what I want to do. An executable. A binary is an executable, so I'll call it a binary. If you're using JetBrains Rust Rover like I am, you can use this, and basically That's how to set it up. So I click on create. It's going to set up a new project for me, but I can also do this, right? Okay, you know what? I'm going to close this. I'm going to delete this project. Not supposed to do this. All right, you know what? I'm going to delete this project. Automatically delete the project. I'm going to go to Rust Rover. I'm going to delete this. So I'm going to start again. Yeah. So I'm going to close this. So I assume this doesn't exist anymore. So what we're going to do is remove from this, remove. So I'm going to open my WAP again. I'm going to cd. I'm going to ls here. I'm going to cd to Rust Rover. So now I'm inside my Rust Rover project. You can use any project any directory of your choice. You can install it to any directory of your choice. This is my own directory, and I'm going to add it here basically. So in this case, I'm going to create a new project like we have here, cargo new this. So I'm going to just type cargo new. So that's basically how to create a new project in Rust. In case you are not familiar, like I said, it's going to be beginner friendly, so this should be very easy. So I'm going to create a new cargo project. I'm going to call it my Bevy game, just to use the examples. When we are about to create our another project, we're going to call it Bevy 101, but for now let's call it my Bevy game. I'm going to create my Bevy game, and for a start, you are free to call it whatever you want. In fact, I'm going to call it Bevy 101, just to be sure. Already have that. Yeah, I think I know why. All right, so I'm just going to call it a new name, cargo new my Bevy game. Basically, what I'm going to call it, I'm going to cd into this directory. That's my Bevy game. Yeah, let's index it. So skip. Now just ignore all of those things I just did now. All you need to do is just run this to command, cargo this. Everything you are seeing here is just AI being embedded into everything. So which is good. We are going to use a lot of AI here to make life easy for us, because you need to understand how to use AI to make your workflow easier, to make life easy for you. You don't need to write as much as before, but you need to understand what you do so that you can guide these LLMs on what to do to write the best code for you. And if they don't do what is necessary, you can always re-guide it to the right path. That's why we are doing that. So after we've done all of this, we've seeded into this. Let's check the directory and see what do we have. We have the cargo.tomo and we have the src. So two things we are going to do. I'm going to open the web storm within this, right? Basically. So if I run cargo run to build the project, you see hello world. Let's try that first. So if I run cargo run here, you can see it's running this already, hello world. So now let's check how we have hello world here. We can do that from the terminal by just doing this vi src main.rs. And you can see there's hello world here. This hello world that you see here is what was printed just now, but we don't need it again. So we're just going to quit this. So basically, I don't want to use the terminal or the command line for this. We want to use an IDE to make it understandable. We don't need to be moving and coming between, IDE screens and terminal screens rather. So let's move into an IDE. I'm going to be using Rust Rover, like I said. So I'm going to be using Rust Rover within this project, and I'm going to start on the Rust Rover instance. So it's going to open that for me automatically. Then, if I'm not mistaken, not now, trust project. Yeah, so we're good. You can see now I have it set up again. So this is another project. You can see it's similar to what we had before. So same thing. And you can see this target folder was created because I ran cargo run here, right? You can see it did this. He said running target this. So what he did was he compiled this project, compiled it. After it was done, he created it into target, right? And then he ran that. So if you check target now, you're going to see that. Okay, fine. You're going to see that target has a debug folder, right, that contains a lot of things, which is this Bevy game. So if I run this Bevy game now, look at what's going to happen. Okay, I need to define this association. So but basically what is supposed to happen is supposed to give me that same hello world that was written on the terminal again, and it's going to do that. So this is exactly what we are going to do. So this is just to explain if you are new to Rust. It's not something crazy. Don't feel scared of it. Rust is just like any other programming language. It's like JavaScript, or let me say TypeScript in this case because it's typed, but it's not actually TypeScript. Don't mind the analogy, but it's still a programming language that you can learn and you can use to build cool stuff. right? And Rust is versatile as much as Python is versatile. So if you're familiar with Python, you can sit very much with Rust because they have similar syntax. If you're familiar with TypeScript, yes, you can still write Rust because you already understand how types work. If you are very familiar with TypeScript in terms of like using proper typing, right, defining options, defining like using very very good TypeScript internals, then you can work with Rust because it makes a lot of sense. You have struct, we have interfaces, just like you have types and interfaces in TypeScript. You have struct in Rust that you can use similarly, right? And then you can extend. Basically, you will see what I'm talking about. Let's not talk too much about that. So yes, now let's go into the game properly. And to do that, what we need to do is to add Bevy. Remember, we said we need to add Bevy as a dependency for us to use it. Currently, we just have something we can use. If you go back to source, you can see what we have here. Let me increase this so that we can have like let's go to the editor of the font size. Let's call it 20. 20 should be nice, right? But basically, let's increase it a bit more. So yeah, enable ligatures. I like using ligatures just in case you don't know what it is. I'll show you when we get there. So I'm going to apply this. I'm going to use this. Is this big enough? I think it should be big enough. Just to be on the safe side, let's increase it a bit. 25. Yeah. So yeah, this is 25 pixels. This should be enough. So this is the function I was run. When we run that, we saw hello world. So if I run this again, I run this on my terminal, you can see hello world. The same thing that I had here. You can literally see cargo run, finished dev profile, not optimized for this target and this. And they added it. He ran the target, my Bevy game, which was what I showed you other time. Debug this. My Bevy game is an installer, is a binary. Is a binary that can be installed. And whenever you run this binary, you should get the hello world because this was what was created. So whenever you click like on Windows way or even on Mac, when you click an application, that means you can basically create an application using Rust that you just double click and it does this for you. We can test it out and that basically should work. Let's see if I can test it out here. Okay, let's go back. I don't have that open, but then we can. Let's do this. Let's open in terminal. Oh, okay. It's supposed to open in my Finder rather, not terminal. Sorry about that. Yeah, reveal in Finder. So let's do this. Let's run this. Run the Bevy game. You can see what is here. It's an executable file, right? So if I double click this, it's supposed to run hello world for me. You can see popped up that. What did you see here? You can see basically did. Let me increase this. You can see it did hello world, saving session completed, deleting expiring sessions. Same thing, right? But the difference is it doesn't give me all of this verbose thing that was given when I ran. Where was I? When I ran this, right? You can literally see that it's a bit different. But then what does it do? It gave me a hello world. So similarly, what we are going to do is that whenever we write our game, we are going to build it and it's going to give us an executable that you can just double click on and it should pop up the game just like you have elsewhere. And then you should be able to run it. Simple and short. So that's why I said Rust is not hard. It's just the way you look at it and maybe what you've read online, but it's basically very simple, like extremely. So let's not go there for now. That's not that's not what we are talking about now. So I'm going to close this and let's focus on building Bevy. So the next thing we need to do, like I said, is to let me remove this. I don't want to have too many things running. Let's see, what do I have? 1, 2. Let's close this. 1, 2, 3. Okay. So let's go back to the browser and add Bevy to my cargo.toml file. So the cargo.toml file, if you're not familiar with Rust, is where you install your dependencies. If you're familiar with TypeScript, this is your package.json file. If you're familiar with Python, it is your requirement.txt file. Or now in newer frameworks like UV, you still have a requirement.txt file or where you install your packages. So cargo is more like your pip in Python and like your PNPM, your package manager, npm, Born, Jan. Cargo is more like inbuilt into the language, so you don't need any other one. You just need one and it works. So you can see the package is similar to what we have on the browser here. My Bevy in their docs rather. My Bevy is 0.10 this, and they have dependencies. Dependencies are empty. So what we need to do is to add Bevy to the dependency. So how do we do that? Like I say, we just need to run cargo add Bevy. It's as simple as that. So that means you go back to the terminal. We can increase the terminal to run cargo add Bevy. I should be able to increase the size of this guy too. Okay. Let's see if I can increase the size. Yeah. Let's call it 18. I think I prefer that. Apply this. Okay. Yeah. So this is big enough. So you can see cargo at Bevy. Literally what we have on the browser here, cargo at Bevy. So you can add it manually too by doing this. But you are not sure of the latest version, so just want to do the add so that the latest version is automatically installed for you. So what we need to do is just cargo out Bevy, and so when I run it, it's going to update the crate. This is called a crate. It's going to update that with Bevy. So just look at it now. You're going to see it added it automatically for you, 0.16.1, which is what was added. So the reason why I don't have this is because if you look at the one on the browser, it is 0.17. But the reason why it installed 0.16 is because my Rust version is 0. I'm still on 1.86. I'm not on the latest version yet. I can install it now, but for the sake of this, I don't want to do that except to really hit a roadblock. Then I'm going to go back to install it, then proceed. But for now, let's just focus on getting this thing done. So we've successfully added Bevy to this. So you can see a lot of things that was added just by that single command. You can see we have a lot of stuff installed. You can see first updating the crate, then adding 475 packages. So 475 to 1.86 compatible version. So it's added all of those things. It's always a good idea to use the latest version. So what that means is I'm supposed to install Rust or update my Rust, right? But I don't know if I want to do that now for the sake of you guys. I don't want to delay you guys on this call. But like I said, if you get to a point where we need it, we can always update Rust and then we update Bevy to the latest version if there's anything we need that's not currently working. But for now, let's just continue with this since the version has been installed that matches my Rust installed version. So that makes a lot of sense, right? So um okay, so in this case, we have Bevy installed automatically based on what we have in the docs. So these are performance optimizations, right? So it might not be an issue for simple project like what we are trying to do for now until we start building real games, but you can always add this also. You can add, it says, let me just read through this. It's not common for debug builds using the default configuration to take multiple minutes to load large 3D models, right? But fortunately, there's a fix. We don't want to give up for fast iterative compiles. You can just add this, right? But for now, I don't think we need this. Reason is because we are not working with something large. But it's always a good idea. You can always add this so that you forget it. So what I'm going to do is just back my logo like this, and that's it. Now, that was everything here. So in case I'm not 3D game project, yeah, I'm still not going to have all those issues of compilation and build times basically. So yes, now let's go to apps. We've set up everything we need, we've done the installations. Now it's time to go into apps. So how do we do that? Very simple. Now, like I said, remember in the beginning when I said Bevy is actually very simple, right? Even from the docs, they said it is easy to pick up. And that's because it has a very good structure, the ECS that I explained, entity component system structure. So what we need now is we need to build apps. How do we do that? So what we need to do is simple. It says in this place, we want to build apps. Every Bevy program can be referred to as an app. Why? Because a game is an app. We call it game app. Every of us are used to calling games apps, right? Even though they are games. So in this case now, you can call Bevy to an app. And how do we do that? All we need to do is go back to our Rust program. So now I can collapse. I can close the terminal until I need it again. So I can close the cargo.toml. We are done with that. So in this case now, your main.rs file, which is where you write which is the entry point to your Rust program, is where we are going to start from. All we need to do is to add the Bevy, this Bevy app and initialization to it. So rather than copying and pasting, I'm just going to do this. You can see no main function found in crate. So there needs to be a main function every single time. There needs to be a function main inside of it. So what I'm going to do in this case is, because we are working with this, right? I'm going to call this. I'm going to start by using use Bevy prelude. You can see this is already adding the autocomplete for me automatically. So use Bevy prelude this, but it's telling me it's unused currently because it's actually unused. So if you look at it, it's similar to what we have here, right? Now, this is just the way you import in Rust. In case you are not familiar, you can see unused import. We don't use the import keyword, we don't use the export keyword in Rust. We use the use keyword in Rust to signify that we are importing something. And what this basically means is we are importing Bevy, we are importing prelude. Prelude is like a sub package in um, in Bevy itself. Now it also has some functions or some modules that you want to import for preload, which is why we just tag it star. Remember, if you are familiar with JavaScript, you will see things like import star from this, or import this from as this from this as a library. We do that a lot in JavaScript, TypeScript rather, when we write whether backend or front end TypeScript. We do that a lot, or mobile, right? So basically, if you're familiar with that, yes, you are very, very familiar with this also. If you're also coming from the Python world, or most let me use those two because they are very, very familiar to people. If you are coming from Python, you've seen things like from this, import star from this. That means you're importing all the packages. So the same thing happens here. We're importing all the packages in preload, which is also a sub package in Bevy, right? That's basically what it means. We're good to go. Don't worry, we are going to talk more about it, but for now, we don't need that. These are just the documentation for Bevy that we can use and stuff and stuff and stuff. So, yeah, to run a new app now, what we need to do is remove the hello world that we had initially. Remember when we added the hello world, we were able to set up a very basic um, terminal hello world that was displayed on the terminal as the execution of our application. This time around, we are running something else. We are running a Bevy instance. So that means we can call this app new run. So what do? App, call it new, right? And call it what? App new run. So sorry about that. You can see this. So we are going to call this. I don't want to add all of these ones here. So we are going to go back to this, and then we are going to call it what? Dot run. So in this case now we are going to run this. You can see it's a function, it's a method on the run, right? So if you do this now and we collapse this, or we close this, we are going to have something like this. Now let's run this to see what we get. Now if I run this main directly from here, and you're going to see what I'm going to get. It's going to compile all of this again, right? And it's going to be opened. Now, compiling is just the first time thing you do. So, because remember we said Bevy has alt reload. If you're not familiar with alt reload, it's simply a way, it just something you have on. Shish. Okay, so two things. I might need to install, update my Rust, because I think there was a time I installed a nightly version of Rust. I was using it then when I was testing how to build an operating system of some sort. Oh my god, long story on that aspect. Jeez. All right, you know what? Give me just few minutes to update my Rust so we can use the actual package in this case, because I feel like this will not work. I don't want to have to debug. We are too early in this time to start debugging anything. So yeah, so just let me do that. Coming. Update my Rust version. Oh yeah. So just this shouldn't take long. We will check through it before. I know how to check Rust. Oh my god. Okay. This is version 1.8.6. 1.86 and then 1.86 if I'm not mistaken. Yeah. Okay. So let's see. Yeah, version 1.86 if I'm not mistaken. Alright, so why it does this thing? Let me see. So yeah, 1.86. So what we need to do is to install it to 1.88, which is what Bevy needs. So we need to install that. We need to also update Bevy. Then same thing, same thing, same thing. So just similar to what we had before. So hopefully this should be. And I say this is WAP. So WAP can be a lot if you're if you just need something simple. If you need something simple, you can stick to Ghostly, or you can use the normal terminal on Mac. I prefer to use WAP when I'm doing something that requires me to multitask a lot, because that's the AI feature I can ask. Sorry if I have to use AI for everything. You guys should understand that that's what works these days to make life easy for us, so, as developers. So yeah, basically just give me like 2 minutes to get this installed and then we can proceed. Yeah. So uh, 35 seconds, 33 seconds. Should be faster than this, but then okay, we'll stick to what we have. So basically, let's go back to this. And once we do this, right, and we run this, we are supposed to, it's not supposed to throw an error that we got the other time. So in the project folder, you notice that nothing happens, right? This is because we haven't told our app to do anything yet. Apps are just empty shells capable of running application logic. So this app that we saw here, right, is just what is coming from preload. Remember we said star. So app is actually coming from preload. That means app is coming from there. New is a method on app, and then run is also like that. So we have all of those things joined together just like a chain, but don't worry, you get used to it. Rust makes things easy and saying it makes it complex at the same time, but then it's understandable. So what makes an app in this case? Before we complete our installation and update, okay, I think it should be done. Okay, this will take a while, so let's proceed. Oh, 1.92. Okay, that's fine. So what makes an app? What sorts of data does our app really store? Right. Remember we talk about the ECS. Please remember the ECS because it's going to be very, very important going forward. In fact, across the entire building process is going to be you are going to understand and need it. So looking at the docs linked, we find three fields: the word, the schedule, and the runner. Now, the word field stores all our game data. Remember, now this first thing you should understand is when we talk about words in game dev, basically when we talk about word in game dev, we are simply talking about let me call it words in game dev simply means it's basically just like this word that we are, right? Think of it like the earth that we are is a word. So when we talk about word in game dev, it's just a way of representing the actual word. That's the physical word, but in a virtual manner, in a virtual form. So that's basically what the word is. The word feed stores all our games data. The schedule holds the systems that operate on this data and the order in which they do so. So what does that mean? If you want to schedule, just like we have a work clock, right? You know that once it's 2 o'clock, let's say you have a task set for 2, you already have a schedule for that 2 o'clock. If you have another task for 4, you have a schedule. That means you automatically have a schedule for 4. In this case, now you can create schedules within the world. So that means you can create a world that simulates this actual physical world that we are. So that means you can create an entity for everybody that exists, right? Myself, yourself. You can create an entity of a game of yourself, right? That have schedules, that can create schedules for the day and that keeps running every day, that keeps growing, that keeps interacting with other people. So it's basically just a model representation of the physical world, but then you translate those actions, those events into a virtual world. So that's what a schedule is in this case. The world, remember, it stores all our games data. So in this, imagine that the world, this earth that we are, is a game. All the data in this game are going to be the trees, are going to be the water, going to be the earth, going to be the houses, going to be the structures, right? Going to be the cars. Those are game data. The humans, everything basically you can think of, this from the smallest to the largest, those are our game data. Everything you can imagine that you can see, that you can touch, that you can feel, that you can create, that you can burn, that you can destroy, they are all game data. So you can think of it as our game data. So if you are simulating the earth as a game, you know what you need a lot of data for that. So you need to build the roads, build the structure, build the maps, build the continents. They are all game data. So that's very important to understand. The next thing is the schedule. The schedule holds the system that I've already explained the schedule, right? And then the runner interprets the schedule to control the broad execution strategy. So that means if you have a schedule, like I said, for 2 o'clock, 2 p.m. during the day, and another for 4 p.m., you already know that you have two schedules for that day, one for 2, one for 4. What makes it different or what makes it significant is how do you run them? So the runner understands how they should be executed, what the runner is. So we have three things, right? So what does our app really store? Our app will store these three things. So it stores the words data, stores the schedule, and stores the runner that executes the schedules. So basically, we are still going to do more on this, but we are going to do more on it by building. So generally, you'll be operating at a more granular level than these basic primitives, controlling data in terms of your own specific resources and adding systems to an existing schedule. To do so, let me read this again because I need to point out some things. You generally be operating at a more granular level than these basic primitives, controlling data in terms of specific resources or components, that's the component from ECS, and adding systems to your existing schedules, right? So to do so, customize your app by chaining its method with the builder pattern. Now, the builder pattern is very interesting, and if you're not familiar with the builder pattern, it's most of us are familiar with it. If you're familiar with TypeScript, it's that thing you always see in TypeScript where you can chain a lot of things. You can have things like, let me just put that in the comments. You can have things like await. No, okay. You can have things like, let's say this is an await, it's an asynchronous function, right? You can have it like call me, right? Dot then this is a builder function. Dot then dot hatch, right? Something like this. Now you can see that I'm chaining this together. Now this is not a perfect example of a builder pattern, yeah, but it's to explain what we want to talk about. A builder pattern in this case is something similar to this. You can, if I wanted to run this again, I can run something like app dot. You can see the example I had the other time. Dot new dot add plugins dot run. I can add dot new like this, right? I can have dot. You can see all the things I have here. This I can add event dot. I can have all of this again. I can under event dot before I can now run this. Do you understand? You can see that it still works. That means I am adding and adding, and so this is basically the builder pattern. So if you are coming from JavaScript, you can see it's similar to this. So if you are coming from JavaScript, yeah, it's basically the same thing. So let me comment this. Let's see our installation. Oh, still going. That's why we want to do this. But yeah, let's continue exploring the docs while we wait. So it makes use of the builder pattern. The most basic tools are initializing resources in the world. Remember the world schedule and the runner also. Initializing resources in the world. Remember the world is where you store the data. To store globally available data that we only need a single copy of. Globally available data. Don't forget that. Adding system to our schedule, which can read and modify resources and our entity components according to our game logic. And then importing other blocks of apps, modifying code using plugins. So don't worry, we understand all of these things. Now we'll cover a bit more of this in the next pages. Speaking of which, we are finally going to add some logic to our game, to our app. Let me call it app now because we call it app in Bevy using Bevy ECS. Now, this is where we talk about the ECS a lot. Remember, I said keep track of it because it's very, very important all through your understanding of Bevy. So, ECS, we already understand that it is the entity component system, right? It's a paradigm that's used by Bevy, which is which what I've explained, right? ECS is not just a paradigm of Bevy; it's a software pattern like that we use in programming. It's not Bevy is not the first to use it; it's just using because it seems logical to use the programs into these things and chain them together. And it's because of the ability to have them like this that you can chain them together. Why? Because you can have them as methods. Methods can return that the other method can call and return. So it's just a very simple process of, let's say you have like an hierarchy of a class, then your class has methods, the methods can call another method, the method can call another method until it gets to like variable or functions or whatever. So it's just a pattern, the builder pattern, the chained pattern in this case. But in this case, we call it the builder pattern. Things like languages like Java is very common. Languages like Rust too, we have that we can make use of it, and we definitely will make use of it in Bevy using Bevy framework. So busy Bevy engine. So now what are we talking about here? So the ECS entities are unique things, like I was explaining at the beginning, that are assigned group of components, right? Which are then processed using systems. So I think this is the easiest way to understand it. Remember when we were explaining that entities here, right? Okay, I didn't write it, but then entities, like we said, are like the humans. The components are like the attributes that you define for us. Let me not call it attributes. That's not the right word to use. Or okay, let's go with that for now. We assign things that makes us who we are and that makes us to be able to interact with others. And then those things are processed using the systems, right? So that's basically the way to understand it. So entities are unique things. The trees, let's look at the world, the earth example again, whereby the earth is a general virtual place, right? As a general virtual place, we have entities like the trees, entities like the real world, the cars. Okay, yeah, cars to entities. You can have them as entities like humans, like the animals, right? As a dog is an entity in that case, a cat is an entity in that case, and they have their components that that makes them what they are. So that way you can call them the components. And now, how do you process those components? You use the systems. That's the explanation here. So, for example, one entity might have a position and velocity component, whereas another entity might have position and UI components, which is similar to what I said. A human being and a dog, for instance, are both entities. In this case, a human is a mammal. A dog also, okay, fine, let's not use the mammal keyword. A human has certain properties that dogs don't have. So in this case, a human has both position and let's say velocity. Yes, a dog also has position and velocity. But if you look at the car, for instance, a car has position, velocity, but doesn't have something else that a human will have. So in that case, you can look at them as different entities, but like they are the same, they are entities in the game, but they have different components that make them what they are, even though they are both entities. Does that make sense? That makes sense? Yeah, something like that. I think I'm keep looking for the analogy that best explains it, but I think that does justice to it. So systems are logic that runs, right? Remember at the beginning we said that systems are the logic that you run on specific set of component types. So you might have a movement system. System are just functions. In fact, let's simplify this. System are functions. Component are tree as structs. So let's say you have a struct now, like a human being that I am. I have my struct. My struct is something that defines me, right? As a human. So let's say as a human, I have my name, I have my age, my gender, my race, all of those things, right? Let's not even use race now. Let's say location in the world, right? I may be in any part of the world. Now that is part of where we are. Your race is part of who you are. Your geology, geography is where you is part of who you are. So all of those things are things that you specify as my component or my struct for my entity. That entity is different from an animal entity. Even though we have similar entities at that point, there are still unique differences that makes us different in this case. So that's basically so the struct is what you refer to as components. Component that you define on the entity. And then the functions are just systems are just functions that you define just like you define a function or you implement a function for a struct in Rust. That's basically what we are talking about here. We see it in action. So ECS pattern encourages clean decoupled designs by forcing you to break up your app data and logic into its core components. So that's why Bevy went with the ECS pattern. Like I said, it's a software pattern. Software engineering pattern is not just tied to Bevy. So if you're not familiar, you can also check it to understand. So that's what happened here. Why is my Rust having errors? Oh no. The Rust update mostly does but encountered a minor error at the end. It's self-update permission issue related to this. Let me verify. Why is my Rust pro? Ah, jeez. I haven't used this new. I haven't encountered this error anywhere. Okay, let's try this. Let's see. Am I still in my Bevy? Yeah. Cargo Bevy. So let's add Bevy to this and see if it has updated the Bevy. Let's check now. Cargo. Okay, let me just update this. So I'm going to update this, right? So if I cargo run should automatically update to the latest one. So if I cargo run again, so watch what is going to happen here. So it's basically just like the way you have package your JSON and then you install package your JSON and then you wait and it installs and update your dependencies. That's basically the same thing here. So let's go back to the documentation because we are almost done with the significant parts of what we need before we start writing the code. So this year's pattern we already understand encourages that component breakup, right? To make it easier and decoupled and clean, right? It also makes your code faster by optimizing memory access patterns and making parallelisms easier. That is very important. So parallelism is easier because why you can break your code into sections. You know what is what and what cannot be accessible by what. So that way you can ensure that this and this can run parallel to each other without having issues, without bottleneck, without race conditions. So that makes a lot more sense, right? So it can also help you to make your code faster, right? You already understand that parallelism make your code faster, optimizing memory access patterns. Why? Because you know that what can access this and this. So that means you can prevent bottlenecks and risk conditions, like we said. So that's that. So now let's jump into the actual thing. I just hope my Rust issues has been fixed. So let's go into the actual thing. Bevy ECS is Bevy's implementation of the ECS pattern. Unlike other Rust ECS implementations, which often requires complex lifetimes, traits, builder patterns, or macros, Bevy ECS uses normal Rust data types for all of these concepts. Now, let me take that again. Bevy ECS is Bevy's implementation of the ECS pattern, right? Unlike other Rust ECS implementations, which often requires complex lifetimes, traits, and builder patterns or macros, Bevy ECS uses normal Rust data types for all of these concepts, meaning that you don't need to worry about traits. You don't need to worry about complex lifetimes. You don't need to worry about builder patterns that already exist in Rust that are native to that and macros. So that means we are not dealing with all of this complexity. That's why I said as a beginner, you can pick it up. Does that make sense now? So if you still feel like this is getting hard now, this should give you a bit more relaxation or confidence in yourself that you can pick this up and you can understand it. Bevy CS uses just normal Rust data types, and we are going to brush across all of this. Trust me, like this is beginner friendly for you, whether you are starting Rust today or yesterday or tomorrow. Trust me, it's going to make sense to you. So now let's start with the components, right? Like I say, components are just structs. We already established that components are structs, systems are functions, entities are still structs. But then there are structs that the definition of the entities are the components, and then the functions that defines what those component does is your systems. Simple and short. Now let's go into that. The components are what raw struct that implements the component trait, right? So that means that's why you have the derive. So they've already handled all of this complexity for you. The lifetime, straight, macros has been handled for you. So everything you interact with are just basic data types. Basic data type in the sense that you have the struct, you have the functions, you have the normal data types, integers, floats, all of those other ones, booleans, and the rest. So that's what you interact with to write Bevy. So it makes it extremely simple to write stuffs, complex, powerful things, but in a simple way. Makes sense. Yes. So now let's proceed. So like we establish components, and you can see this is a macro, right? Um, so it's already established. So what this does now, what the component does, this component, you can see that we are deriving component here. We are deriving this component. Simply means that what this whatever whenever you write, whenever you add this macro, right, to any struct, you are simply saying that um you are simply using all that been implemented for the component. So that means you are tagging this as a component, first of all. That's what you are doing. First thing you are doing is you are tagging this position as a component. Understand that. You are tagging it as a component. That's why you are deriving the component here. And because this was already implemented, the component trait, you don't need to re-implement the trait. The trait already has everything that you need, which we are going to look at if you want to. But for now, let's focus on this. And then we have this struct defined. So the struct defined is just what? Inheriting everything that the component has. Do you understand now? So you are simply by adding this, you are simply saying that this position is a component in Bevy. And then these are just normal basic data types, float F32 and F32, meaning the float position, float data type. Simple. Then the systems, remember, are just normal functions, like we said, they are just normal Rust functions. And what does that mean? It means you can simply create a function here and give it a name, just like you do in normal Rust program, right? And add in an argument here. We add an argument to it, and what is that argument? It's called query. And what does the query mean? Query is coming from what? Bevy itself. There's something called query. Remember, we mentioned something about query initially at the beginning. Let me okay, I don't want to go back there, but then we said that it's a data-driven framework. So that means you can query data. You have a query. Um, I don't want to call it a trait. No, it's not a trait, but you can actually. It has a very rich query system built into Bevy itself that allows you to be able to query stuff. And that's why you can see that this is already, so this is more like a type on the position type, position struct. So that means query in, you are simply typing it as a query type that you want to query what's the position. That means you are querying with this struct that you've already defined. And so what do? You can just look through it to say that for position in query, means you are looking at each of the data in this each of the field in this struct. You're simply saying for position in query, and this add sign simply means it's mutable. Remember that. Okay, if you're not familiar with Rust, whenever you see this sign here, the and sign in Rust, it simply means you want to be mutable. Mutable in the sense that you can update it. In Rust, you can't update a variable just by declaring it. You have to specify updating it. It's part of the strictness of Rust. Don't worry, we'll talk about this in more detail. So we now say for position in this, right? You print the line of position this X and Y, basically. So now let's talk about entities now. So when we talk about components, components are just struct, right? That implements the what? The component trait. By adding this to it, you are defining this as a component. Systems are just normal functions, but then they're taking the parameter of mostly query, mostly. Then we have the entities. Entities are just simple depth type containing a unique integer. Basically, they're just a struct that contains an integer. They are not defined like this. Now let's see how this works in practice. Now let's practicalize this. Now we've done all of this. We've installed this. Let me try running this program again. Let's go here, cargo run. If everything goes well, we should not have any errors. Now, fine. There are no errors here, so that means everything works fine, right? Yes. So no problem, no errors. If I run this again, there should be no error at all. Why are you taking so much time? I'm building it. Oh no. Sorry about that. I'm supposed to run. Yeah. So basically, we just write cargo run and then we should be able to run this. Not build, run. This is building, but then it's still the same thing. You shouldn't have any errors. You can see It's fine now. So we can collapse this. So that means installing, updating the Rust fixed the issue we had the other time. So now that we are done, we've already covered everything we need to from the doc also. Now let's jump right into writing code. So the first system. Now we've already written our first app, right? By writing this. Now let's write our first system. Now we can paste the following into our main.rs file, but no, we are not going to paste this. We are going to add it into it. So we are going to be writing as much as possible. So let's write this. What do we need? Hello world. So I'm going to make this smaller. I'm going to collapse all of this so we have more room space so that we can have more information to work with. So we are going to call this hello world, right? And print line like this. So in this case now we have a function defined. This was the original function we had initially from the beginning, right? But we are redefining it again because now in this case now this is our system. It's our system. It's just a function. Doesn't matter what. This is our first system. Now remember in that also we had our main function defined. Remember that the main is the entry point. So this one is also a function that we define as a system for our game. So now what we need to do is the remaining step is to add it to our app. Right? Remember the builder system, the builder pattern we talked about. So that means now instead of just new.run, what we can do is we can chain the hello world to it. How do we do that? We add systems. Now let's do add. You can see the options we have. We can add message, add observer, add plugins, add schedule, add systems, add audio source. These are functions that we can add. To what? To our new, right? And to our app itself, which the new is the way of initializing the app, right? So we can add what systems. That's what we need. So adding system is basically what you can see is implementing app is a function. Add system is also a function. Basically, if you look at it here, it's a function on what the app. So you can add systems, and what does he expect? He's expecting this it's itself as an instance. So he's expecting the self as an instance, and then the schedule. So basically, he's expecting the schedule and system. We are not going to pass the instance since we're already defining it on the instance already. So what we just need to do here is just say add systems. And what does that system do? We are going to be adding what? Hello world. Nope, but not directly. We are going to be doing what? Add update. And then the update in this case is the schedule. Remember we talked about schedule, word, and what? Runner. Exactly. Now in this case, now we have the hello world. The hello world in this case is our function that we want to run. So that means we are scheduling using an update. Now remember, if you are over on this again, what does he expect? He's expecting parameters of what? Schedule and systems. Two things. Like I said, we are not going to be adding self. Why? Because we are already chaining it to a new. We are chaining it already. So it's already passing the self directly to add systems. So what we are doing is update. Update is of what type? Let's look at update. Pop struct update. Now, the schedule that contains any app logic that must run one per render frame. For most gameplay logic, consider using fixed update instead. But right now, don't worry. We'll come to all of this. Example of systems that should run once per render frame include but not limited to UI, input handling, audio control, and stuff like that. So this is basically what we are working with, right? It's simple as that, as simple as this, no stress, no problem, justice. And as we have this now, let's try running this again. If I run this again, okay, I don't want to run the coverage. Let's just run this. Don't tell me you are building. Okay, it's not. Now you can see it has what? Hello world again. The previous time we ran it, there was no hello world. If you check, you can see this was the previous run. Now that we've added the system to this and hello world, is automatically we are calling this schedule on it. So that means when we add the system, we are telling it to schedule this. So this is going to remember when we talk about update, it runs any logic once per render frame. So what does that mean? We are calling the hello world on every render. So whenever we run the game, it's going to be calling hello world on the first render, or not on the first render, or when you render per frame, or let me say once per render frame. Okay, this is confusing, but then it means it runs once. That's basically what it means. So update means to run once. So let me say yes, run once is perfect in this case. So we close that. So now you can see the power of this by chaining add systems to it. It basically works. I don't know if that makes sense. So that's basically what we need to do, and you can see that's all. So this function add the system to our app update schedule, which was what we talked about, but we'll cover that in more. Exactly, we also covered that more of that later. Now, if you run our app now, just as we did, we will see hello world pretend to the terminal, which we had before. which makes sense. It simply means our app is doing what it should do and is working as expected. Okay, so that means we are good to go. What we are working on is making sense. We don't have any issues currently, and everything works as expected. Now let's write our component. The first thing is we've done our systems. We've seen how system works. Now the first thing we want to do is write our component. Now everything we've done so far is just basic Rust programs, right? And you can see we've written functions. So even if you're not familiar with Rust, now you understand that all you need to do is write a function and you can chain it to this. We are going to talk about more of all of these things when we get to actual using modules and stuff. But we're going to talk about that, which should, like I said, be easier to work with. But we're actually going to write a game today and show a screen, right? So tomorrow again, we're going to have another one by this time, same time, and then we are going to proceed from where we stopped today, build something more complex, and that's how we keep doing it every day until we are familiar with what we are doing, and then we can try out things. So probably before the end of the week, building stuff like this every day, we should be able to do more, be comfortable building a program or a game that we can actually run. You can do it yourself and stuff like that. But let's focus on the on what we are doing for now. So let's work with the components, right? So greeting the whole world is great, but what if you want to add specific people? In ECS, we generally model people as entities, just like I was explaining the other time, with a set of components that define them exactly. Now let's start with simple with a person component. So what we need to do first of all is to define. Remember, I said we need to actually add the component macro to it to specify that what the struct we are defining should inherit this component trait, which simply means it should inherit. Okay, which simply means you are tagging it as a component. Let me not use all these complex words. So basically writing, let's start by doing this. Add this struct to your main.rs file. So I'm going to copy this too. So let's derive component. In this case, component struct person. Now we are just defining the struct person. In this case, now it simply means that what we are defining this person as a component. But what if we want our people to have a name, right? In a more traditional design, we just tack on a name, string field to person. But other entities may have the same names too. Might have names too. For example, the dog should probably have a name. Remember the dog in the animal person analogy I was giving? This now you see where it comes to play here as entities with components. Do you understand now? But other entities, in this case now the dog is an entity that may have a name. That means the name that we are defining, those are components for them. Those are their properties. For example, dogs should also have a name. It often makes sense to break up data types into small pieces to encourage code reuse. So let's make name its own component. So that means we can do this also. I'm going to duplicate this. So I like using shortcuts a lot, so bear with me on that. Name. So we're going to call name like this. So basically, we are defining the name component and passing this parameter to it, which is a type of string. So it means that name should expect what string. So now we define name already as its own component. So that means now we have a person component, we have a name component, so that can be reused for different type of components. So that means if you have a component of person, you can also have a component of what? Animal. Do you understand? So that means we can use name on both animal and person. Don't worry, we'll see how to do that. So we can then add people to our world using a startup system. Now this is important, please. Let's focus on this. We can then add people to our world using a startup system. The startup system are just like normal systems, but they run exactly once. Remember this system we added the other time? Let me go back to this system we added, which is this function, right? We add systems, but in this case now we can add what? Startup system. Startup system are just like normal systems, but they run exactly once before all the other systems. So that means you can have multiple systems. Now remember we have the update here, which is like the update scheduler that is defined as a system. Now in this case, we can have a startup system. Now in this case, let's call this an update system that updates once per frame. In this case, now what if you want to have something that updates immediately we load the game? That is what we call a startup system. Does that make sense? So basically, don't worry. This is building a game and writing Rust. Is a combination of both, and it's going to be interesting if you continue just the same way we are trying to do it. So let's proceed from here. So the next thing is let's use command to spawn some entities into our world, right? So we can define a function again, right? And which is going to be of a command, is going to be a command function, but then don't worry, we understand what we are talking about. Let's proceed. So we are going to write that function. So all of this is our, don't worry, just let's leave it as it is now. Let's write this function have people. So command dot spawn. The spawn is, if you understand spawn in game development, spawn basically just means like you are creating. Spawn means create. Yeah, let me just use that word. Spawn means create. So in this case, you are creating a person, right? And a name. Remember the name, that stuff we talked about, like creating a struct. Do you understand? So we have to struct person, name, they are both components, right? So in this case, a name we always take in a string. So let's call it the same name, Elena Proctor, right? Let's call it the same thing, Elena Proctor dot to string. So the first one is done. Basically, what this means is that we've created our first command that will be created. And that means the first thing that we are doing here is we are creating a person, giving the person a name. So we are spawning a person component with a name called Elena Proctor. The first person that will be spawned or created is going to be a person with a name. Don't worry, these are like fixed stuff. So it's something that you can reuse multiple times. So you can, I'm not creating an animal, but then you know what? There's no point in this. Let me just duplicate this and give it a different name. Renzo Hume, right? And call this Zaina Neves, like this. So we are done with this three things. So what this means is that we are spawning people. So imagine a game whereby you have a world like I explained. You want to model the physical world in a virtual setting. You know that when you want to create humans, you can use this as a way to create humans. You can spawn them with a name, a default name that can, or you can spawn them with a name that becomes the identity. So this is basically how you can do something like that in an actual game. So trust me, game development can be easy and can be fun, but okay, let's not go there. So now let's register the startup system. Remember, we said we want this to run immediately the system starts up before any other system like this. So that means what we want to do is we want to, I can break this down into stuff like this. There's no need doing this. So let's add this system, add systems. But in this case, it's going to be a startup system, right? It's going to be a startup. You can save startup, pre-startup, post-startup, but we are using a startup system. And then the startup system we call what? Add people. So it's going to add people, and then we are chaining what to it. We are chaining the add system, the second add system that is updating, and then we are running the app itself. That's all. So that's all. Now you can see that what we did here is we created the person struct, name struct, and we have used it in this place, basically. So that means by adding this component, if you see the spawn, what does the spawn do? The spawn takes in what? A bundle type. So you can see that in this place now, Bevy has already handled all the lifetimes issues for us. You can see implement lifetime. This tick that you have here, let me not call it tick, a single quote that you have here, or apostrophe sign that you have here, are called lifetimes in Rust. You can see it here, entity command lifetimes. They've already handled all the lifetimes, all the complexity for you. All you just need to do is create data structures. That's the simplicity of Rust at the highest level, and the complexity of Rust too at the highest level exists. But if you know what you're doing, you can abstractions that that hides the complexity, which is basically what every programming language does. So that's why Bev is a very, 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 very beautiful framework, because it hides away all those complexity for you to build simply. Every major beautiful frameworks you know of, that's what they do. Like Django in Python, like what even React, right? React in JavaScript or TypeScript, they hide all of this in the abstractions. You don't see some of the crazy things going beyond behind the scene, but they make it easy for you to do. Like React has a lot of those things. You know, modifying the DOM for you without even thinking of it, using state, using effects, using all of those things. Those are abstractions. The same happen here in Bevy. You have abstractions everywhere, and that makes a lot more sense. So, so you can see this is just using spawn. We can use something called spawn batch for better performance, but let's understand all of them before we actually start speaking about batches. So that's basically what we are doing. And then, like you see, the way we combine different components here, right? We can combine different components. We can even create a new component with a component bundle, calling it something like this, a component, a component. So, but let's not go crazy here. This is basically, so now when we run this, what do you think is going to happen? If you can guess. If you follow what we've done so far, you should be able to guess what the result or the expectation should be. First that's going to happen is what, let's try it out. We are going to see the results. So just to make it easier to understand, feed zero is never, no, I'm not using name. Animal is used, but okay. Let me, I forgot this is Rust. Yeah, it's as straight as it comes. So basically we've done everything we needed to do, right? We've done everything we needed here. We've created our name struct as a string, derive the component, give the name string, and we've used that inside of this place. Name this to this, and basically everything else. So now if you run this, you're still going to get an for this. Let me move this here. You know what? Let me move this like this. Okay, so let me move this. Let me put this struct up here. Right. Don't worry, I'm still going to increase this, like make it full screen so it's easy to understand. So let's try run this again. I'll go run. It's going to give, like I said, it's going to give that. Now I'm getting my hello world again. Now the question is, why am I getting the hello? Don't worry, I'm going to understand this. Now, my first query here. You can see this actually spawned this person. This, and this. Actually, this is supposed to give me another definition. It's supposed to give me another value entirely. What happened here? Mute commands. Yeah. Name this. Yeah, I can spawn different things. Basically what is here. And that works. So I can spawn it using the name. So where is name coming from if it doesn't take it? So why are you refusing to take the string? If it's zero is never used. Huh. Okay, I think I understand what is happening here, but then you're not going to bother about this for now. We're still going to work with it, but let's not bother about it for now. We're going to come back to it. Okay, so feed in this struct. Let's see. He's asking me to derive it. I already derived it. Okay. So yes, we have that already. So we'll come back to this. Let's not dwell on this for now. Like I said, it's too early to have things that are going to be dealing with very early. Right. It's part of development. Things like this happen. You find errors, you fix it. But for now, let's move on. So we have to string just like we have the names, we have the string, we have everything defined, and it works. So now let's register the status system. We've done that already. So the next thing is, which is what we did. We added startup, add people, then the hello world, same thing. So your first query, we could run this now and the add people system will run first, followed by hello world, but our new people don't have anything to do yet. So let's make a system that properly grades the new citizens of our world. Remember that we just all of these guys, right? So let's add the function called grade. The function is going to do what we want. So let's say people with person. So in this case now, for name for those that are coming from Python, you can see that it's actually very similar to how you loop in Python. So you can print this. So print line this and this. So what we want to do is we just created a command called greet people that takes in, remember the query stuff we talked about. So the query takes in a name. The name is the struct you defined here, right? And it takes in with person. Now, what does this with person do? Now you can see that with here, in this case, filter that select entity with a component. This can be used with a query. So it basically means that you are what's the way to explain this best? Okay, so you actually want to be sure that they have a component without actually what's the way to explain it? Okay, you want to be sure that entities have, so you want to select entities with a component, but you don't care about what the component contains. But you want to be sure that name as a comp as a person component also. But you don't care about what person contains at all. You only care about name. So that's basically what this does. Don't worry, we'll use it on other places too when we talk about other things. But for now, we are querying just the name aspect. That's why you see that we are only using the name here, because we don't really care what person is about, but we just want to be sure that it has person and there's person there exist. We will talk about why we need such eventually. So in this case now, it's going to say hello, whoever the person is, for the person we are spawning here eventually. I know it seems a bit complex now, but then we're just getting to the juicy part. It's not going to be complex by the time we continue. So the parameter we pass into the system function define what data the system run on. In this case, group people will run on all the entities with the person and name component. You can interpret this a query above as iterate over every name component for entities that also have a person component. Exactly. Iterate over every name component. That's for entities that also have a person component. So that means both must be true for this to be true. So that means there must be a person with a name for this to pick and to loop through them. So whenever it's picking, this is just a query. Remember, a query is just a way of fetching stuff. So you're simply saying that fetch name that has person that only have a person also. So both must be true for this query to be true, to resolve to true. So that's basically what happens here. So we just registered the system now in our app, just like we had before. So in this case, I'm going to add it to greet people too. So if we add this, so in case of people that are coming from Python, this is basically similar to when you have tuples, right? Exactly. So it simply means you're adding both of them. So we have hello world and greet people in this case. And in this case, now running our app now, let's see what happens. Now you can see we have hello this, hello this, hello this, and hello this, and hello world. Now, why do we have this hello world here? Remember, we still have the hello world function defined, which is hello world system. Then we have the greet people system. Now, in this case, now we spawn certain people here. Now, what we are simply doing is we are picking the people we spawn at the beginning, even though we don't need them immediately, we spawn them, right? But remember that we just spawn them and give them a name. Nothing is supposed to happen automatically. But after we spawn them, what did we do with them? We now assign them a name. And that's why we see that we have to put this immutable stuff here. Well, we are not using it directly, but what we are just simply doing is that we are giving them a name by taking name 0. Name dot 0 in this case means that we are taking name. If I run this now, name is going to be for each of the query. It's going to be picking the names that have person. And how many names have person here? A liner proctor has a person. So what do we mean by that? We pick the name and we get the first instance of that name, which is a liner proctor, Reina, this, and this. So does that make sense? So spawning a user at the beginning, like I said, you can use it to create humans that then have a name by default or that can be assigned names by default. Imagine if you are building a model of our real world, of your physical world. That's exactly what we are doing here. Okay, so that makes so now you can see that we have this. So if you check our, we can see this, and this. So in this case now, the hello world then greets people. So if we now in their own case, you can see that hello world came first. In our own case, it came last. Why? Because what it was just showing, it was running in parallel. This is because system run in parallel by default whenever possible. So that's what part of the parallelism I talk about. So it has a very, very strong um parallel functionality built into it. So it makes a lot more sense. So that's the first thing we've done. So currently we've built our first query. Now in this case, now let's build a mutable query. I don't want us to dwell too much on this, but we're almost done with it. So let's just finish it as much as possible. So let's build our first mutable query. Now, from what we've done so far, you can see the power of Rust already and ECS too, of Bevy, because all we need to do was just create a function, add it to the function, have a logic, have a flow of what we want to build. In this case, we wanted to spawn people by giving them a name, right? So we spawn 3 people. So it simply means like you are creating a space. If you are creating them in like a pod, I'm leaving them in the pod. So the moment you have them or you bring them out, you are greeting them by giving them this. I don't know if that makes sense to you. So the moment you bring them out of the pod, you are greeting them. Oh, welcome to our virtual world. Oh, welcome to our virtual world. Oh, welcome to our virtual world with the name you've assigned to them when you're creating them to the pod. That's basically what we are doing in this case. I just want you to be quite imaginative when you are imagining this. So now let's write our first mutable query. If we want to change the names of some of the people, perhaps they got married. Remember, now you see where I'm talking about the game. So it might be you can model it to someone's to how we live in the earth currently. That way, you can just model it in such a way that what if the person has a name and then he gets married, the person's name will automatically change for a lady or for a guy, depending on where how the logic is being written. For example, we can do this using a mutable query. So, how do we do this? Let's update people. Let's write the function for that. So, we're going to write the function for this and call it what? Update people. Now, it's going to be a mutable function, right? We are going to add mute to it. Why? Because we are adding that to it. So what I was talking about, I think I made a mistake somewhere when I was talking about this as mute. Oh, sheesh. All right. Adding mute to it simply, this is simply a way. This simply means you are making reference. I'm so sorry about that. Simply means you are making reference to it, not to your mutable. I'm using it as a mutable. Simply means you are making a reference. This sign here. Sorry about that. So the mutable keyword is actually using the mut keyword, and then that works here. So what we are doing is we are creating that. So we need to add, because we want to mutate the username. So we want to write with mutable query of query using the mute. Remember, we still use this name, taking a reference to name with person. Same thing. I'm sure that's what is here. Yeah, you can see that. It's just similar logic. The AI can guess because it knows what is expected. So we can have the for mute name in mute query. Why? Because we also want to do something similar to this place. But in this case now, we are going to add name to be a mutable function so that we can modify it. And I'm going to add query as mutable so that we can mutate it also. So we are going to, what do we want to do? We want to update the name. So we are going to say if name dot zero dot, we don't know if it ends with is what the logic is about. Well, let's see the logic equal to a learner proctor. Or in this case, we can say it ends with hum. Let's do our logic. Let's change it to this. If it ends with hum, let's change it to something else. Let's change it to home. Right? And then what do we do? Break. Because it's a loop. We can break out of the loop. Immediately we get what we don't need. So it simply means we don't need to change any other names. So once we get what we need, just break it immediately. Don't consider yourself running the other function. So if it is the first one you see that contains it, just break out of it. If so, that means if you have like 10 names, you don't need to loop through all of them. Run the first, even if you see it at the first one, break it and let the execution stops at that point. So in this case, now if we run this again, we are going to see if it ends with what hum. In this case, we are changing our logic a bit from what they have, but we are still updating it to this. So it's going to change the person's name from Renzo Humes, yeah, to Renzo Home. So let's do that and see. Sorry, we've not even used it at all. We've not used the function at all, so it's not going to do anything yet. We need to add it first to our systems before it can work. So what do we need to do? We need to make query mutable and use a mutable reference. That's the reference I was talking about. Now that's that sign. This sign means reference, not mutable. So when you add it with mutable, it means mutable reference. So whenever you see that sign, it means you are making a reference. So you know if you're familiar with the reference value word in software engineering, like you copy by reference, copy by value. That's basically what is happening here. Simply means you're making a reference to name. You are not working with the actual value. You are working with a reference to the actual value. So it's more like you're making a shallow copy of the actual value or a deep copy, depending on how it was defined. Okay, enough of those technical stuff. Let's not deviate from here. So let's use a mutable reference to the components we want to change. Now, don't forget to add the systems to the update schedule, which simply means we cannot make this, we can't get anything from here until we add it to the system, just like we did here. So what did they do here? They added it and chained it together. Now, why did they chain it together? Note that we use chain on the two systems. This is because we want both of them to run in exactly the order they are listed in the code. Remember, we talked about parallelism the other time. So because we don't want this to run before this, because we don't want the greet people, the update people to run before greet. We want it to greet them, then update them, or we want it to update the people before greeting them. So that way, the update is done before it displays it. That's why we see that we have it like this. So with update people occurring before greet people, if you want it to be the other way around, what is going to happen is you first greet them, then update it. But that way you don't see the update by the time you print it. Now, if they were in, the name might change after we greet the people. Exactly. So, but we don't want the hello world system
we don't add the hello world system to the chain because it doesn't matter when it runs. This way, Bevy can run hello world in parallel while the other systems are running. Now, you see the power of Bevy that we're talking about. Everything can be controlled, defined. So that means you can add parallelism, you can stop parallelism when you need it, you can define to prevent race conditions and bottlenecks. It is perfect in that regard, and it makes a lot more sense. So let me increase this and let's add this to it. Let's add greet people and update people to this, and then chain both of them. And then we have what we have before. So running this, what should we get? Just like they said, it will update the username and then print it. So you're going to see Reina home, not Hume anymore. You can see home, and that makes sense. So currently we have successfully done all that we need to do. We've written our code, we've understood the ECS system on Bevy, and now we can look at other things. But like I said, it's important to look at these things so that you understand when we start reading the code and using some of the examples to write our own game, because we're going to write a game that displays something and then we're going to see it just like a normal game that you play on your laptops or on your mobile phone, but something for this first one, for this first part of this series, let me call it a Rust series, for the first part of building this build series, because they're actually going to be building stuff in this series, building different things, and building not just Rust in this case. We are going to be building a lot of things, but in this series is for Rust. There's other series for TypeScript. There you are building different things, building mobile apps, building complex systems, and showing you how to build it and using AI to speed up your workflow also. But don't worry, we'll talk about all of those things. It's going to be a daily thing. So subscribe if you have not for that so that you don't miss out on it. That aside, so let's look at plugins. We've already understood ECS, we've understood world component systems, we've understood schedules, we've understood systems and how they are being rendered, and how you can chain them, how you can run them in parallel, how you can define them. We understand all of those things now, I believe. So let's talk about plugins. One of the Bevy's core principle is modularity. Now, all Bevy Engine features are implemented as plugins, collection of code that modify an app. This include internal features like the renderer. Remember the renderer I talked about, but games themselves are also implemented as plugins. So all the features of Bevy are implemented as plugins. Yes, don't worry, we'll talk about that more. So this empowers developer to pick and choose what features they want and they don't want. They don't want a UI, don't register the UI plugin. Want to build a headless server, don't register the render plugin. So exactly. So that means you can actually build a server using Bevy. Why? Because it's an engine. Remember, it's just an engine. It's a game engine, meaning that it is built to be able to handle stuff and run very, very, very complicated software or application. In this case, you can use it to build a game. You can use it to build an headless server, even if you don't want a game. Right? Even if you just want to build something that runs on the terminal that is extremely fast, that handles a very high workload, you can use Bevy to build it. That's just the beauty of it. Now, you want to build a headless server, don't register the render plugin. So meaning nothing will render until you want it to. It depends on your logic at all. And then plugins are just things you plug in and plug out. Basically, just what it means, plug-ins. That's all. This also means you are free to replace any component you don't like. If you feel the need, you are welcome to build your own UI plugin, but consider contributing it back to Bevy if you think it will be useful. So that's why I was saying that if you're an expert listening to this, all you can do is contribute to Bevy. It will help a lot so that beginners like we and intermediate gross developers can also make use of it and like learn from it. Build something very, very cool with Bevy, make it into a full scalable solution that can build games or complex applications. Like that makes a lot more sense. That is useful. That that solves problems, and can also contribute to just that ecosystem, other product that exists. Contribute to the ecosystem, Rust ecosystem generally. Contribute to developers. Become useful for whatever you want to use it for. Now, those not contributed back into Bevy and instead released separately are third-party plugins. So that means you can have third-party plugins also. They are useful and easy to add, to use additions created by fellow developers that can help to avoid reinventing the wheel. To use them, all you have to do is what? Find a third-party Bevy plugin like those at the assets page. We are still going to come to that. Add it to your cargo.toml file as a crate, just the same way you added Bevy. Import the code definitions from the crate to your workspace. Add the plugin to your app. just like you have plugins. Just like we did something here like add systems, you can also add plugins. Remember I showed you add plugins the other time, like this. Exactly, you can add plugins, any plugin you defined or you want to add, and it works the same way. So that's all. So, but most developers in the custom plugin and just for the full engine experience with no hassle. And Bevy provides you a set of default plugins. We can look at all the default plugins that Bevy provides us with. We'll check that out eventually. Now you can see all of this. Bevy provides us with panic handler login plugin, logic plugin, tax to plugin. There are a lot of plugins that you can use. So, like I said, it's optional. You can plug in, plug out, whatever you want or not. But in this case, we can make our app interesting by adding Bevy's default plugins, which are a plugin group containing core engine features. For those needing minimal features, minimal plugins exist. Add plugins, default plugins add this feature most people expect from an engine, such as 2D, 3D renderer, asset loading, a UI system, windows, and input. Do you understand now? So all those things are plugins as well. So it's something you can remove. If you don't want sound, you can totally remove. I'm sure you can remove the sound down plugin. I don't know if sound is a plugin, but I think you could do that. Let's see. Yeah, audio plugin. You can totally remove that if you don't want to. You are at liberty to do what you want. It just makes it easy for you to work and to make sense, to build things that you just want to build. Flexibility is there, while still making it powerful enough to build whatever you want. Yes. So now it says, let's make our app interesting. Currently what we have is just UI. There's no pop-up, there's no window, but we are trying to build a game. So where's the window? Right? So let's do that. All we need to do is add a plugin called default plugins. So how do we do that? Let's add it first. Add plugins, default plugins. Default plugins are just like we said here, they are plugins that are already created by Bevy. There's a minimal plugin too, but we don't need that. We want the default that allows us to be able to see windows like we defined here. So if we run this again now, we should see a pop-up now. Yep. You can see it keeps running. You can see this keeps running. As long as the window remains open, it will keep rendering this. It will keep rendering this. It will keep rendering this. You can see. So because it's a game render, right? You keep rendering this. So this is the window. And the moment I close this window, it should stop. That's it. So does this make sense to anybody? I know if it does, please just drop a reaction in the chat, and so I can know that you guys are following, because it makes a lot more sense. Right. So that's basically what we are trying to do. So yes, and yeah, that's basically how you can display a window with Bevy, like that, just the simple thing. So even if I remove all of this, right, if I remove all of this and I run this plugin, just the plugin, what do you think I'm going to get? I'm still going to get that, right? Because even though I don't have any of these functions running, it's still going to run my window for me. I'm going to see it working. I can expand it, I can minimize it. It's an actual window that runs. That's it. Okay. We're done with that. So I'm going to add these systems back. You can see the plug in, plug out functionality. See how flexible it is to add stuff to it. All right. So now let's go to the main thing. Yeah, let's go back to the browser. So two things you can see. It says window pop-up, which is what I've shown you guys. Native window actually. Then the console fill of the logins, because the schedule now runs in a loop once per frame. Remember the once per frame that we talked about in the update? That's why. So it will keep running once per frame. And remember that as a window is just something that renders multiple frames, because it refreshes multiple times. So as it refreshes, you keep seeing those things that you saw here, happening. They keep refreshing. That was when you saw the other time. So that's basically it. So yep, and to give you your system information, all of those things, we don't need that here. So yeah, that's basically it. So creating your first plugin. Let's create a plugin for ourselves now, because we've created a system for ourselves. We've understood how to plug in systems, and that's taught us how to write functions, how to write structs, and so we've learned two things. We've learned how to build a game window, and then how to write Rust, even if you're a beginner. So let's write a plugin now, just to show you how more experienced developers write their own plugin for what they want. Just to give you a taste of it, you might need it faster than you think because when you start building stuff, you might not see what you want. Then you should understand how to build it rather than waiting. Right? It gives you that flexibility. So now let's understand how to write your own plugin. So creating your own first plugin requires you to use the plugin to implement the plugin, right? So there's a plugin interface that you can implement. Remember, I talked about struct the other time. So you can implement that, and because it's already written for you. So basically, let's just skip that and write the code. It says we move all our LO logic to a plugin. To create a plugin, we just need to implement the plugin interface. Yes, and the following code to this. So we are going to do that ourselves. So how do we do it? Let's create a plugin. Let me call it an app, not a game. So we are going to implement a, why do I forget? That's not on the other screen. We're going to implement a plugin, right? Like this. Implement plugin, but we're going to first define a plugin like this, pop struct. So let's do that at the top here. Hello plugin, right? So pop struct hello plugin. So we're going to implement this. You can see implement plugin for hello plugin. So we're going to implement the you can see not all traits implemented, missing build. So what do we need to do? We need to implement what? The build function. You can see that that's the first thing they did here. So that makes sense. So build is just a function. So you can see the simplicity of Rust. Like even if you're not familiar, you can see what Rust can do for you. So it simply means you define the build function because we need to implement the build. That means build is implemented in plugin by default that we also need to implement. So that's what we need to do. So add things to your app here. That's all. So you can see the same thing. We have a self, reference to self, which is what we have here. We have the app and the immutable reference to app, and the mutable reference to app, rather, not immutable, the mutable reference to app. So we can do this, and so which is basically the same thing they did here. So this is how you write your own plugin. So if you want to write a plugin for the hello world, just like we have here, the hello logic, that's the hello world logic that we have here. Now you can register your plugin like the same way we register the default plugin. So we just call it something like, even though it doesn't do anything currently, you can register it like this. So you see the flexibility of hello plugin. I didn't call it plugins. You can see hello plugin, and that's it. So if I run this now, it's still going to do the same thing as before, even though this is there. Nothing changes. So now note the add plugin can add any number of plugins or plugin groups like default plugins by passing in a tuple of them. Now all that is left is to move our systems into hello plugins, which is just a matter of cut and paste. The app variable in our plugins build function is the same builder type we use in our main function. That is where the builder pattern comes in. A copy and paste just works because we already have an instance, we already have a reference to what the app. That's the same app we're adding to here initially. So what we need to do is, let me show you what we're talking about. So we already know that add systems here is changed to this. Like, remember I was saying that this is an instance. So that means the reason why you're changing this is because it's returning an instance of itself, which is this app. Now this new is like you're initializing a new app. So it's returning an instance of itself that allows you to be able to chain it to other things. It's basically the way it works in all languages. Literally the same way. So now that means what we can do here, we can just remove this, copy this out, or if I cut this out and paste it into the build. Paste into the build. And but what do? We use the app. This app that we have here, we use that automatically. Now, and you can see this. So we have the self and we have the app, mutable reference to app. But in this case, it's not chained anymore. So we need to end both of them. And then you can see just by copying that automatically just works. So we can replace all the add systems to just replacing it with a plugin, and that works 100%. Does this make sense? I see the simplicity of our program here and how Rust can help you make your work easier, make it easy to use. Like not just easy in this case, make it simpler, easier, usable.
So in this case now we are adding systems to it. The same thing we have. So let's try to see if we have the same result as before. We see that it will pop up the window and it keeps running the log, the hello world and the hello names log for every frames per render. You can see. So for every render of the frame, it's going to keep displaying this. So nothing changes. The only thing is that we created a plugin instead of a system that we used. And that makes sense. It still works as before. Nothing changes. And you can see. So in the next section, we'll fix the hello spam using resources. Now, we are building this. We don't want to just jump into building a complex game. We need to understand the basics, but still writing code to understand the basics. Then we jump into the actual game, build an interface, and then we call it a day. Then we come back the following day, which is tomorrow, and build something else and chain them subsequently. So, but for now, let's understand all of this information and use them to understand more. So let's create the resources, which is the next thing we want to do. So in this case, a resource, what is a resource? We've already talked about entity and components, which we understand. And now we talk about systems, which we understand. We talk about plugins, which we understand. Now, the entity and component data types are great for representing complex, queryable groups of data. Now, this may look like a lot of words, right? A resource, just like the name implies, just means a resource. You want a resource. So let's say, for instance, you want to build a shack, or let me say, you want to build a table. You need a resource for the table. What do you need? You either need a screw, or you need, if you're using nails, you need nails, you need hammer. But if you're using a screw, then you do not need an hammer for that. You need a screw, you're going to need a tape, you're going to need the woods. Those are the resources you need. So in this case now, resources are ways of what's the word? What's the word to represent this now? Okay, yeah, just like the way I said, you need for you to build a table. Okay, in this case now, the table is your entity, right? You can look at it that way. You want to build a table, you want to use an entity. You know that a table requires a lot of things. Your resources for building that table, you need your hammer. Let's say you need a screw. Let's stick to the screw. You need a tape, you need a screw. You probably need a pencil to draw and to be able to understand the dimensions. So you need those three things. Those are your resources. Now, the same thing applies to Bevy. Your table in this case can be entities. The components for the table you already understand. It must be this height, it must be this, it must be that. It might be complex, but because you can use the resources to manage the complexity. So you can use it to manage. This is not the perfect analogy. Don't worry. You just with this understand resources that you need for a particular entity, it will make sense. Now, but let's just look at this. It said the entity and component data type are good for representing complex queryable groups of data, but most apps will require globally unique data of some kind. In Bevy CS, we represent globally unique data using the resource trait. Here are some kind of examples of data that could be encoded as a resource. The elapsed time, the asset collection, sound texture meshes, the renders. Similar to what I just explained. The pencil that you have is what you need to mark stuff. That means you use it globally for the entire build. The screws, use it for the entire build. The hammer might not be needed for some things, but it's still a resource. So that's the same thing. Now in this case, now you say tracking time with resources. Let's solve our app's hello spam problem by only printing hello once every 2 seconds. We do this by using the time resource, which is automatically added to our app via add plugins, right? For simplicity, we remove the hello world system from our app. This way, we only need to adapt the greet people system. So that means we can basically just comment or remove the hello world because we don't need it. Remember that we still have it. We can always add it whenever we want, but for now, we don't need it, right? So we can remove this unnecessary parentheses. So resources are accessed in much the same way that we access components. You can access the time resource in your system like this. Same greet time stuff. So how do we do that? Now we need to modify the greet people. The greet people, we want it to be printing these guys every 2 seconds. So that means we need to add it to the query, this function here. So what we need to do is not just the query alone. We need to add the resources to the query. So in this case now, if we want to build a table, just like we said, we need resources. So we need resources for that particular problem. So that means we need to add the resource in this case, which is time, right? We need, which is time, to what? to the particular problem we are trying to solve. So that means we need to tag it as a resource. You see the way I'm adding it now. We know that we need time, so but we need to actually initialize it, give it a variable type. So we'll say time, and I call it time. So the type of time is what? Of time type. Then we need to pass it as a resource to time, like this, basically. So when we do that, we are simply saying res time. That means this is a type of resource. Time is a type of resource, and so time resource time is let me say is a variable of resource time is time. So you can use time to represent this, but it's fully typed. Simple. So we have this, then we say for name inquiry, which is basically what we have here before. What do we now want to do? We want to modify it to do something. So now we can access time from here. So if we want, we are not using it currently, but we are still going to get to use it. So let's go back to our doc. We say, so we have res and res mute. Res mute should give you an understanding that whenever you want to mutate, right, the resource, then you can use res mute. So res and res mute pointers provide read and write access. This is first read. Mutable allows you to write, like we said, to resources. So nothing has changed. So the delta field on time gives us the time that has passed since the last update. But in order to run our system once every 2 seconds, we must track the amount of time that has passed over a series of updates. To make this easier, Bevy provide a timer type. Let's create a new resource to track elapsed time with a timer. So how do we do that? We create a what? Resource to track elapsed time with a timer. If you want to track something, maybe the time it takes you to build your table, you need a stopwatch. A stopwatch in this case is also a resource and is used for the same thing, which is the entity. Now you see the complexity of you trying to build a table and the resources you need. Now it's the same thing that applies. Just have to model it to a real, then you know the pieces you need, then you now plug it into building your game. Now this is the way you want to think about it. But basically, remember we're using this to learn Rust as well. So you can see how simply it is to actually put the pieces together. But don't forget that this has been abstracted for us. But this is what you need to be able to fully understand the power of Rust before diving deep into the lower levels to write it. Because if you don't understand how everything can be put together, you cannot write what we put them together like this. It's just a piece of advice. So then let's go to the next thing. What we need to do is to make it easy for us to implement the 2-second functionality, we need to create a resource type. So let's create a resource type and create it up here. Before the plugin, let's create it as a derive. Create it as a resource and call it what? Let me see, what name should we give it? Great timer. And we give it timer. Perfect. Like this. Right, you can see. So now we are simply saying that grid timer is a type of what? Resource. Name is a type of what? Component. Or let me say it's deriving from component. It's not a type of. Okay, don't think of the type of as a technical term. It's a type of component as a generic term now, not technical. Isn't that thinking of it as a technical term can make you feel wrong, but let's ignore that. So greet people as our function. What do we need to do here? It simply means we use so now we can update this greet people function, update our timer with the time elapsed since the last update. Remember, we want to update it to make sure it continues to print after every 2 seconds. So we need to use the timer. So update our timer with the time elapsed since the last update. If that caused the timer to finish, we say hello to everyone. So that's it. So this is what we need to now do to our to the greet people function. So before we loop through and display the name, we want to check if the time has elapsed. So how do we do that? We need to check, we need to play the timer. We don't need the parentheses in Rust. I keep forgetting, sorry. TypeScript can make you stick to that. So we need the time. In this case, we have time, but we need to also have the timer. Why? Because we want to make modifications. So we already have the time that makes you read. We need the timer also that makes you write. So we need the res mute, right? And for time in this case. So in this case, we need to put great timer, not time. We are just reading time here, but now we want to modify the timer. Remember, the timer is of what? Is a resource type. So timer should allow us to be able to do that. So timer dot what? What do we need now? Dot 0 dot tick. Time dot delta dot just finished. So yeah, these are function names. Like you don't need to cram them, but it's good you know them. So I don't also remember them like most times, but it's always good to have them. So I'm going to add mute timer here. You can see because this is a mutable type. So it's just Rust is common sense to always add mutable to whatever you want to mutate. So you can see same thing. So it says now all that is left is adding a grid timer resource on our Hello plugin. Use timer mode dot repeating to make the timer repeat. So what we just did here is that whenever it runs the timer and it keeps ticking, right? And it ticks whenever it finish ticking, basically that's okay. That's not the way to play. Let's go back to this. Update our timer with the time elapsed since the last update. Remember that this is when we said it's always runs, right? It renders frames every second. So update our timer with the time elapsed since the last update. So whenever the screen updates, you should update this timer. That's why we have the just finish function. So whenever the just finished, it will run this. That's basically what this does. So the timer does 0.tick. The tick is a way of like running every second. It's just like you have the sleep function in JavaScript. So you should run the time.data. Whenever it finishes this, then you should update our timer. That's why timer.tick is updated with this. Yeah, I know this is where Rust gets stupid sometimes, but then this works. So then we have all of this, and the next thing to do is add the grid timer resource to our Hello plugin. So we need to go back to our Hello plugin. I know this seems a bit abstract now, but it's not. Trust me. When you understand how this pieces comes together, then you understand that okay, yeah, this makes sense. So we want to add it to our Hello plugin. So the Hello plugin is where, not here, into the implementation. So remember we have the systems. Now we want to add this before the systems, right? We want to have app.insert resource. Now we want to add resource. What does resource take? Resource take a resource parameter, right? It takes a parameter of resource. So how do we fill it? We need to fill it with a resource. And what is the resource we want to fill it with? Grid timer. Remember, grid timer is the only resource we have here. So we want to fill it with grid timer resource. So it's going to do something else because that's not the only thing we need. So we need to pass in something because grid timer, remember, takes in a timer type. So that means we need to pass in what timer. Remember, we said Bevy has a timer inbuilt timer mode rather timer mode repeating that you can use. But it also has a timer that you can use also. You can see provide the timer type. So which is what we used here also timer automatically. We didn't need to import anything to use it. So timer dot from seconds to 0.0. So it has to be a float. Then the timer mode, which is the timer mode dot repeating once or repeating. I wanted to show you guys what it has, but timer. So we are simply saying repeat this every 2 seconds. So we are saying grid timer here. Remember we said when we're defining this, we said it should tick, and whenever it's finished. So whenever it's finished here means that it should tick with the timer that we passed in, and the parameter that is passed to this is what? Every 2 seconds. Repeat. So that's what this is now. So this grid timer takes in what? A timer parameter. The timer parameter checks and adds what? It calculates from 2 seconds. Continue doing that. So timer dot 2 seconds here, this timer that you see here is the time dot delta that we had to this one. So whenever it finishes that 2 seconds, it's going to run this. So like I said, this is where Rust gets a bit complex, but then you can always use this with AI. That's the beauty of it nowadays. So you don't have to always cram this. You don't really need this. So now let's test it again to see what happens. So that means instead of running for every frame, it's going to run every 2 seconds, just like we have. So it's going to show our pop-up window. Then it's going to render that every 2 seconds. 1, 2, 1, 2, 1, 2. You can see it. So that's basically what we've done. That makes sense? Yes, it does. So we successfully implemented and completed all the resource implementations. So we've done ECS, we've talked about systems, we've talked about components, we've talked about plugins, now we've talked about resources. And now you have everything literally to build your own game if you want to. And also you've learned certain things from Rust based on just this single line of code. You've learned what a struct is if you are new, and even if you are not new, you understand what a struct is. And you see that we are using just data types. But if you are new, you've understood what a data type is in Rust and the types we have. We have a struct, which we have used. We have we have used this, right? We've used a macro, right? Because it already has a trait derived from us, written for us that we derive from. So we use macros, we use struct, we use functions, right? You can see the chaining pattern in Rust that we have that we can use. You can see the functions, that's the defined functions, pass parameters. You understand what the mute keyword is. You understand what a reference is, what a mute is. Then also you understand a lot more than that. You understand how to use this, right? Because you're simply saying that, oh yes, you're using this with a particular type. In this case now, query is a struct. So you are wrapping another struct with a struct to give it meaning. So you can see all the complex things you've done just in one day, just by learning how to do stuff. And then we've also learned on that thing how to implement a struct, right? Exactly. So that's basically what we've done. So next step, what is the next step? Next step is to use the examples. And the beauty of this is the examples gives us a way of writing stuffs ourselves, right? So say we want to what's the word? You want to build a game, but you don't want to start from scratch. Yes, the example gives you a perfect place to start. And then from there you can just proceed and keep trying. So that's the interesting thing about it. So you don't want to bother yourself, but it perfectly works for your use case, whatever the use case is. So yeah, so that's that. That's basically everything we need to start Bevy and to understand Rust. So now we spent about 2 hours on this. Let's say roughly 2 hours. We started around 4:30 something, usually 6 something. So in 2 hours, we've been able to understand the entire Bevy, what you need to get started with Bevy and Rust, even if you're a beginner. And now if you decide to build something, we can do that. So if there are any questions from anyone, we can always use this to conclude, or we can try out an example just to see how it works. Depends. If you have a suggestion, please feel free to just point it out and let's trash it before we proceed.
Okay, so yes, I think now that we've done this, this makes a lot more sense. So the beauty of it is we can do an example, right? Let's start with an example. So since there are no questions, no nothing to stop with, let's implement an example. Something simple, not too crazy. Implement the example and show you an example. It's a sample game, and then we show you how that can work. Show you the code, try modifying it for the first part, just to give you a taste of what you want, what you're supposed to expect from Bevy. So that by tomorrow or in the next part of the series, we can build something a bit more complex than that. So let's start with the examples. So you can see this is the next step. We've reached the quick start. So basically what we need to start with, we've already covered everything. So you can still do more. You can learn more if you want. It's not crazy or impossible to learn. Definitely not. So we can always do that. And that also means we can, yeah. So now let's start with the example to avoid a lot of all the small talk. Let's start with the Bevy example. So I'm going to open this in a new tab so that we can always come back to this place. So new tab created. Go back to the new tab. No, not like this. Okay, yeah. So this is the GitHub repo with the lot of examples, right? A lot of examples. So you can see there are 2D examples, there are 2D examples, there are 3D examples. Yes. So that means this is what happens when you like clone the repo. You can run all of them one by one. Like I said, we are not cloning the repo. We're going to try running them on our own, first of all. So the Bevy example is just a GitHub repo containing all the examples. The web examples also works. But let me show you the web example so that you can have a taste of what we are talking about. So this is it. All the examples you see in the GitHub repo, all the 2D, 3D animations have exactly the same thing. You can see 2D, 3D animation app, asset, audio. It's literally the same thing. It's just from each of these. So in this case now, the 2D rendering, you can see how to create a 2D render using. So what do we mean by render? Render basically means that maybe you render a screen in a web page, right? It's just a way of using logic and creating visuals from it, right? But in this case, we're using an engine. In this case, Rust is not just for creating things that you don't see, that cannot create visuals, like the way you write TypeScript to create websites or web apps that we can see and play with. You can also do the same in Rust. And this Bev is one of those things that you can use, right, to create visuals. That's why we call them renders. So it's an engine that you can use to create all of these visuals and all of these things that makes a lot more sense. So that's basically what we are implementing here. And yeah, so that's it. So let's look at examples. The first one here is the 2D render or the 2D viewport world, right? Now these are all 2D examples. There are 3D examples, obviously. Also, we are going to look at all of them. Now, in this case, now this is an example. Move the mouse to see the circle follow your cursor. Do you see? You see the mouse, the arrow following my cursor. This is something you can implement in a web page, but this is not a web page actually. This is an actual application that you can run on your desktop, on your laptop, and it works, right? So you can use command period to zoom in and zoom out. You can see me zooming out and zooming in, making it bigger, making it smaller. And the more I do that, it automatically works. Do you see it now? I can use WASD to move the viewport. I can use IJKL to resize the viewport. Very weird, but it works. You can see it. So, this just works. You can use it to move the camera. You can use the arrow keys. So this is the camera. So the green one, in this case, is like our camera. So you can see that. So now do we implement something like this? Can we implement something like this? That's the idea. Yes, we can. So what we need to do is we can copy this and you can see we can understand this code now. Me looking at it, you can understand it, even if not the entire thing, but you can understand some part of it. So let's look at the first instance. The first thing you see here is what you see let me refresh this so that I can bring it back to the reset state. This is what we have. So now to understand this, It says the example demonstrates how to use the camera viewport to work 2D to create a dynamic viewport and camera. So now we are entering the camera aspect. The camera in this case, when we talk about gaming and 3D worlds or 2D worlds or the world of gaming or visuals or rendering, when we talk about the cameras, we are simply talking about things like what you use to get your views retried. Or let me say it's like an entry point to your views, basically, or your viewport. So in this case now, we're talking about the world. We talk about the world, the scheduler, and the render, right? So in this case, we have a camera that you can use to tweak where you see things from. But because this is a 2D plane, a flat plane, you can literally see from any angle you point the camera to. But from a 3D plane, where you have depth, you can now see, you can have perspective, you can have scaling, you can have skewing, all of those things. So we are going to come to all the 3D part also, but let's start with the 2D. And in this case, where we are talking about the 2D now, let's try to understand just the code itself before talking about the the other aspect of it. Now, the first thing we need to see here is we see the 2D viewport to word. We are going to write this, then test it to see if it gives us the same result. The first thing is we need to import just the same way we did before, import Bevy. But this time around, we are importing the camera on the viewport. Remember, we said we are using the viewports to Word 2D. So we are importing the viewport. In this case, we're importing the camera. We're importing the colors. Now, one interesting thing about Bevy I forgot to mention, okay, not forget because we've not got in there, is that you can actually use very simple color schemes like Tailwind. Like if you're familiar with web design, it sits perfectly right with you. You can use Tailwind like CSS kind of tweaks in your Bevy applications. That's how simple it is to create stuffs and to create renders, UIs using Bevy. That makes a lot more sense. So what first thing we start with here is just the import, right? Basically import everything you need. Import the camera, import the colors, import the math, which we are going to use for making some calculations like zooming in and zooming out, right? All of those things. So we can just import that from Bevy. Bevy allows us to import all of those things directly. Sorry. Yes, Bevy allows us to import all of those things directly without needing to use anything external, right? It has already created a lot of all those libraries that we need out of the box. So the first thing we start with is the main function, which we understand is the entry point to our application. But remember that this entry point now allows us to have this. We have the add plugin. Remember, we already understand what the plugin does. We understand what the default plugin does just by seeing this. We understand what the systems do. That's the startup system. We understand what the fixed update. Remember, I mentioned the fixed update, which is if you want it to run once per frame, separate from the update we used. And then we also understand that we have the post update. The fixed update means it only render once instead of rendering per frame, per every frame, once per frame. It's going to render just once, not per frame. The post update is going to render after the update is complete. Don't worry, we didn't talk about that, but we can always look at it, understand the documentation to see more. But basically, we use the startup here, fixed update, and post update, and we just added functions to it, and that's it. So it's something we can understand what is done here. And what are the functions they use? We use the setup function, the control function, and the draw cursor function. So you can simply see that we can now understand what is here, and we can replicate it, and we can also tweak it to what we want. So it's simple. It's not crazy. It's not difficult to do. It's extremely simple to do. So to implement also. So the first thing here is let's look at the draw cursor function. The draw cursor in this case, remember what our program is all about. Draw cursor is this circle that you see here. It's the same cursor as what I have here, but the moment I enter into this viewport, it creates this circle that follows my cursor around everywhere I go to, and it's literally instant. There's almost no latency to it. So that's basically what we are trying to replicate. Now, in this case, now let's look at how it's been done. The first thing they did was draw the cursor. So that means for me to be able to draw the cursor, I need to know the position of what my mouse. Remember, now we are trying to break down the logic here even before we start reading the code. Why? Because we want to know that if we are to write it ourselves without prior knowledge, using what we've already learned, it's possible. First thing we need to do is I want to know the position of the cursor because that's what I'm trying to implement. So that means after rendering the screen, like I have here, I need and I'm rendering the camera to follow my cursor. in this case. But then let us talk about things we've not talked about yet. Let's just understand we need to track the state of my cursor, which is the important part of it. So tracking the state of the cursor in this case simply means that I need to have a way to follow the cursor on the screen, which is where we now need to talk about the whole was that camera movement, which is what we need to understand. So let's look at the functions. Basically, the first thing is the camera query, which is a single camera global transformation. So the single is also a struct, just like we explained. It's a struct that encapsulates the camera, right? So we understand also that the camera comes from where? Probably from the prelude, right? Because we are not importing it anyway. So, and there's also a reference to the camera. So that means there's a camera already, probably a plugin or something that's already created by Bevy, but it's available to us automatically by Bevy, which is not recreated anywhere here based on what we can see, right? So that means it exists. So the camera, like we already know, there's a viewport like this that we can use. So that exists, and the global transformation also exists. So we have a window, which is a single window also. So the window, the single window is what we are tracking here, which is what we are rendering this viewport in, or let me say the cursor tracker in. So when we do that now, next thing we need to do is these gizmos. Now, gizmos basically is just what's the term to use for gizmos? Let's see. Explanation. Oh no, what did I do? Gizmo. I wasn't trying to go to the tab. So let's go to the gizmo. A gizmo from Google says, oh my god, this is not what I'm looking. What is gizmo? Oh, what is a gizmo? Yeah, a gadget, especially one where the names speaker doesn't know or can't recall. So basically, a gizmo exists in Bevy. Just let's understand it that way. So a gizmo is something that allows us to be able to draw stuff like the circle and all of those things. For now, let's just understand that is there. But remember, we imported this. It's already available to us by from the Bevy's imports, which is what we use or which what we have currently. So that means we have the gizmo here, which is this automatically by default. So now we create a table reference to we create a mutable version, not a reference because it's not a reference. We create a mutable value of gizmos that we can also update. So that means what first thing we need to do is we want to get the camera query, right? So we already defined our camera query. The camera is just a single camera with global transformations. That's what our camera is. So we create it as a tuple. We destructure it. So that means we destructure the camera query to have what camera and camera transformation, which is this and this. So this camera becomes this becomes this. Now I'm trying to explain the code so that you can understand even before we write anything that it's possible for you to think of it and implement it. So the next thing is what we break down the next thing. Remember, I said we need to know the cursor position. If not, we can't implement something that tracks the cursor if you don't know the position of the cursor. That's the first thing. So for us to know the position of the cursor, we use the window, right? And what is the window? This. Remember I said we are tracking it within the window. Remember we are not tracking it across the screen, only within the window. The moment we go out of the window, it stops. The moment we even slide in a little, we can see it's coming up already. And then it shows. So that's basically, so we are tracking it within the scope of the window. Within the scope of the window. So the first thing we do is what we get the window cursor position. So there's already a cursor position method, or let me say function, on the window itself. So by doing that, we assign that into a variable, a Rust type check on it using sum, and then we perform a conditional rendering on that, a conditional check on it by checking if let that cursor position to this. So what we want to do is if that is actually true, is what we calculate the word position based on the cursor position. Now you understand this now. Once we are able to successfully get the cursor position and it is valid, that means if there's no error, getting the cursor position using this sum as a check. If this is valid, this logic is valid. What we do first of all is we calculate a word position. Remember we said that the word in this case is like the viewport. The viewport in the sense that if I want to say my word is in my living room, basically, it simply means that whatever I do within that time or whatever game I'm building exists within
that living room. So that's the word in that case. So in this case, the word we are building here is just that black box on the screen. Makes sense. So calculate the word's position based on the cursor's position, literally. So how do we do that? So remember, we are still checking, making this check. We are saying if the cursor position is valid and the camera the viewport to word 2D, right, is also valid, meaning that the camera, that's this camera instance that we got from here, that we initialized from here, dot viewport to word 2D has the camera transformation and contains the cursor position. That means that's how we get the word position, right? So we also test the camera the word position and convert the result back to viewport space and then back to word space. Don't worry. This seems like all grammar, but then if you think about it, where it makes sense. The first thing you want to do is you want to get the cursor position. You want to know, you want to scope the cursor position to the word's position, the viewport position. And that's basically what is happening here. It is being scoped. And that's why we call it the word position. We get the cursor position first. We get the word position next. Make sure it is okay, right? The next thing we check is the viewport to check that it is actually okay. So how do we do that? We check the viewport also. That's so we test the camera word viewport, word to viewport. Remember the first thing we did was viewport to word 2D. Then we check back to word to viewport. By using the camera transformation also, but we extend it from 0 to 0. So what does that mean? We take this camera, we have performed a word to viewport. Remember, we already got in the word position, right? We already know the word position. So we convert it back to the viewport position by saying camera transformation, word position that we've gotten here, to extend it by 0.0. We understand when we start writing this. And let's okay the word check. So we are, this is the last check we are performing here. If the word check, that means camera the viewport to word to the camera transformation and viewport check, which is this dot xy. The xy basically is the cursor position at the end of the day with respect to the viewport. That's, for instance, now if I put my mouse here, this particular location where the mouse is has an xy position. That's exactly what this is. So that's the word check at the end of the day. So if that is correct, it draws the gizmo. This is where we now draw the gizmo. The gizmo is just, remember that this has two circles, one red and one white. The white is bigger and is outside, the red is smaller and is inside the white. That's exactly what this gizmo is. So if we get the word cursor position and we get the viewport to word position, we get the word to viewport position, and we get the actual position we are looking for, and everything is correct, there are no errors with our checks, then we draw the gizmo to the cursor position itself and give it a color of white and 10.0 basically. So we draw a circle 2D, should be the same as word position. So you can, if you look at what is happening here now, you can see that this first row, which is the white one, which is the one outside, is for the word position. The second one we draw is for the word check. So that means this and this still give the same value. But these are just multiple checks, I believe, just to be sure that they resolve to the same value or the same result. So that's why we're able to draw this. So if you notice this, there is drawing on different places. It's drawing one on the word position and the word check. Word check is the last aspect, which is the word check dot xy, which is the final position of the viewport. That's basically where it's using it. So don't worry, we are going to test all of these, change values to see why we are using all of this. So then the next thing we have is the controls. Now remember, we have controls here, which is move your mouse to see the circle like I'm doing. We use the arrow key to move the camera. So that means it's the camera in this case. This green thing is the camera. If I want to be sure, if I press this, if I press it down, it goes up. If I press up, it goes down. If I press left, it goes right. If I press right key, it goes left. So that means it does the inverse. We can always fix that in the code. So currently it does the inverse of whatever the arrow is supposed to do. But if I press down on the arrow, it goes up. Do you understand? And you can see everything works fine, perfectly well. Okay, so we finally we understand how to draw the cursor now, and we understand that we added the draw cursor to what? To the post update. So now let's look at what setup and control does. Next thing we see is controls. Control, that means it renders only once. and just once. So what is control? What does it do? The control is just all of those stuffs. Click this to do this and do this. So what we need is the camera query here. The reason why we need this is because we need access to the camera to know where to position it, I believe. Then the transform, then the projection. So we need a window also to be able to know the window we are working with, to have an instance of the window. We need the input, basically because we want the key code, right? We want to be able to press our keys and get input for that particular application. And then we need the time. So, well, I don't know why we need time curve for now, but I know we need the other ones. So let's look at the time. Okay, because of the speed. All right. So the controls now. First thing we need to do is we move all of this camera query and we destructure it to camera, transform, and projection. As you can see, camera, transform, projection. Just destructuring. Then we define the speed. So by 600 times time dot data, which is time here, dot data in seconds. Then you use speed. I don't know what F speed and use speed is, but okay, yeah, this is the float speed, and this is the unsigned integer speed as U32. So that makes sense. So now the window size. What is the window size we created? So the window size is window the resolution of physical size. That's the window size. So we simply say camera movement controls input the pressed key code arrow up, meaning that when I press the arrow up key, what happens? It translates to the top. Transition to Y, the Y axis, right? It adds speed to it. What is the F speed? The current 600 times the current time. That's the meaning. So if I press the input, what is the input in this case? The key code dot arrow up. That's why when I press the arrow key here, you saw that it was going. When I press the up arrow key, it was going down. And what does that mean? Let me try it again. You can see how fast it is. The moment I press it, it just increases in speed automatically. So that's basically what is controlling that here. So if I press the key down, it becomes minus equal to F speed. So if we want to change the current movement of that camera, what we need to do is switch this to minus, switch this to plus, and everything should work fine. Okay, so the same thing applies to vertical, the horizontal axis, the X, negative X and positive X. We switch it to and everything works fine. So camera zoom controls, right? Camera zoom controls. Now, the zoom control, remember, is just the way it shows in terms of scale, which is if I click on the zoom, what do we zoom it now? It says zoom in and out. We use the camera, the comma, and the period. You can see that when we zoom in, also it also zooms in the cursor. If you zoom out, it zooms out the cursor. So that means it's using that. Now you can see. So how do we do that? It simply means we are scaling. Scaling in the sense that we are scaling this circle and we are scaling all the gizmos. Let me call that the gizmos. So we are scaling the gizmos, which is these two circles, the white and the red. So we are scaling them. So that's the first thing that happens. So in this case now, by scaling them, we are simply referring to it as well. Projection to the, that's why we needed the projection here. For the camera movement, we did not the projection, we just needed the translation, that's X and Y movement. But in this case, we want to scale. So the only way we can scale is to use the projection that's available already by default in Bevy. So how do we do that? We define our projection, right, by creating a table reference, by making it a table reference that we can access, and then we can make modifications to. So we say if, so we define this, we check this rather, and we say let's projection orthographic projection to the equals to the projection that we got or that we already structured from here. Now, if input or pressed is the key code dot comma, that means the same thing. Scale that projection, right? Scale it by what? Floating power of 4.0 f2 by this. So that means when you click on it, it should float by that. It should scale up rather by this 4 times. So it's going to keep scaling. So if you want to reduce the scale, you just multiply by 0.25 and then continue to increase to reduce in scale. Basically, by multiplying it by what? The time in data seconds. So we are using time because the time always changes whenever it renders changes. So this is what we can use to always change, make modifications, because that way this will always change right? So you can use this multiplication, this time, we can use the time rather, the time the data sequence as our fixed constant that we multiply this against. So anytime, that's why you see you have times equal to. So because this time is going to be there for every render, right? You already know the time per render. So then you can use that to define our up and lower limit for the scale, or the decrease and increase of the scale. So the next thing we want to do is a viewport, right? We say camera viewport. Now, how do you work with the viewport? Remember the viewport we did was the WASD, right? And if I type WASD now, so that simply means this black thing you see here is the viewport. So this is the camera, this screen. The black is the viewport. So if you want to resize the viewport also, we can use this to resize the viewport, as you can see. So the viewport is this black rectangle here. So that's the viewport. So how do we access that particular one? We'd say camera dot viewport. How do we know our camera has viewport? Remember, we've done camera dot viewport to other things before. We used to Word, viewport to Word 2D, and all of those. So that means camera automatically has a viewport attribute or property that we can access, and we set it, convert it to a mutable value, and we set it to a viewport variable. Now, viewport movement controls is if input or pressed key.w, which is supposed to what? Take the value up. That's in terms of move the value of the move the viewport up a bit. What we are doing here is viewport of physical position dot y equal to viewport of physical position dot y dot saturating sub. Then move it up by speed. We've not done anything on saturating sub. We understand what it does. Then that's why it's able to move completely. So in this case, we are moving the viewport itself. That's the physical position of the viewport to in the y direction, the y axis, by this u speed. And remember, the u speed is something we defined here the other time. Exactly. So the same happens when you press the other keys. It changes that, it determines what happens, and that's it. So the same applies to the bound viewport. So bound viewport, so it doesn't go off screen. Exactly. So notice that when you, no matter what you do, scrolling down will not take a screen. So if I modify the viewport down, you see it still remains there. It doesn't change, it doesn't go off the screen, basically, which is what we want, which is actually what we want. So that means that is done. So how is it implemented here? We bound the viewport position so it doesn't go off screen. Viewport of physical position equals to viewport of physical position, minimum of the mean value between the window size and the physical size. So that means there's a window size. And the window size here, we already know what the value is window here, which is the resolution of the window dot the physical size. Okay, so we can do that. View it, bound it to the minimum of those two position, and also the maximum of this new dimension, which is what, if a 2 times vector of a 2 by 2 vector, which is like 2020. So which is how that is being created. So let's go to the setup. The setup in this case contains what you need to run on startup. So the first thing you need to run on startup is what? The window size, which is what is being rendered. Remember, that's the same thing as what is here. Window dot resolution of physical size. Where is it again? Window duration of physical size, exactly, as the window size. So that means if that becomes the window size locally, then we have it here too as well. But this as vector 2. Then initialize send non-filling window viewport. So we create a spawn of it to the camera and the properties of the camera right here. And then create a minimal UI explaining how to interact, which is the exact thing we wrote. But if you think about it, how do we write the text? This is how we did it. We just have a text and create it as a new, and then add the text inside of it. And then we created a node. Now this node now allows us to be able to style or configure it the way we want in the spawn. So we created the node, the position type of absolute, the top, the left, and that's it. So that's why when we created that, you can see that it is here, just by the top left. So that's exactly how that was done. So the setup, creates that, it spawns this, initialize
is this initialize centered node window filling. That's basically what we did here. So command does spawn this. We create a camera 2D, then we create a viewport, give it a physical position, then we define basically defining the camera in this point with the properties. Now the second one here is create a minimal UI in this. We define the text, define the node, then we create a mesh to make the camera movement visible. So the mesh is what? The mesh 2D, which adds and creates the rectangle of size of what? 40 by 20. And then a mesh material 2D, materials that add color from green. And that's how we created that, definitely. So add the background to visualize with viewport bounds. So mesh 2D again to create a rectangle, mesh material 2D to create, to give it color, and then a transformation of that from transformation of the vector 3, which is by a 3 by 3 axis, which is more like a 3D thing. But we are not doing that now because the background, this is the background now to visualize viewport bounds. So we just created the background with a very Z index of 200. Weird. So basically, this is it. This is how to create all of this. And we can test that out by copying this. We can literally copy this example. So let's do that. Let's copy this. I don't want us to have to write this, but we'll make some changes to it. So let's copy this. Let's create our own. I wanted us to be able to create, to call this, but that requires us to do some import and some import. I don't want us to have to do that. Okay, you know what we're going to do here? We are going to the viewport. You know what? Let's see if I can use the analogy used here. Okay, you know what? Just create it. Let's create a new Rust file. To what? To the world. Nah, not yet. So all we did here was to add it as a module, right? Basically, so that means we can, that way we can access it. So yeah, that's why it was asking if I wanted to add it as a module. And I said yes, so we created it as a module, and now we can use it. So if I want to, I can. Let's see. So that way we can just run this, the viewports toward, just same way we run the main. But in this case, remember, even though it has a main, we still can run it by, because we just use this as a module. We import it as a module. So all we can do is let's see. Cannot find viewport toward, which is there. It's private. Yeah, it's true. It's private. Okay, so let's try running this. Okay, nothing else. Literally the same thing. The same circle, the same thing. Let's try writing. Let's try zooming in. You can see, you can zoom in, but it doesn't also leave the viewports. Even if you move it, it doesn't go out of the viewport. It still remains. So we literally just wrote the same thing that was written. But now let's test the old reload functionality that we read at the beginning to see if it works. Let's change the viewports here. Like, you understood that we imported all of this. Okay, even if you don't understand, we'll still talk about that. Let's change it to red. Let's see. Create a new window. Okay. The alt reload doesn't seem to work here. What do I need to do to get alt reload to work? Okay, so you know what? I'm going to close this. Then we're going to run it again. So if I'm not mistaken now, the color should be red. Exactly. Now we see the color is red, like just red, automatically red. So now this makes a lot more sense because now you see that by just doing this, you can see we have automatically everything that we need to make modifications and to even adjust it to make more sense. So if we want, we can create more gizmo to this. So let's try creating a gizmo to this. Let's add more stuff to it. Let's see what we get. Here's the gizmo. Yeah. Let's create another one for the let's see. Let's create another one and call it orange. Yes, let's call it orange, but not for the word check now. Let's create for viewport check. So we can know, let's call it 12. So that is basically the radius is 12. It will be bigger than the white and the red. Right. Currently it doesn't work, so it doesn't automatically reload. So stop and rerun. So let's see rerun this. Then I'm going to go get the color. We're going to see. So that way we can understand better why that is. Okay. So it doesn't create an orange colored one. That's weird. So the view word check doesn't create that, but this one creates the same thing. It should be same as what position. So if you check the cursor position and we create it with the cursor position, does it work? Let's try that. Yeah, still nothing. So okay. So next thing we want to do is let's use the cursor position instead, right? And see if it's going to give us that. Wait, did I even import? Why did they have to add it elsewhere? I not just add it to the first one, which is orange here. Okay, so that doesn't give us what we're expecting. Okay, so everything still works as usual, as normal. Just oh yeah, this is it. I knew the orange was supposed to display, but you can see the difference between this and this. See the color position, and that was why we needed to do all of those things. Now look at what is happening. Whenever I move out of the, see the gap between it. I knew there was something there. So okay, so that's why the cursor position, the window It's just weird. It's not supposed to show there, but you understand now why we need to do it with the word position, right? And then with the word check. So this way we understand that. All right, so let's modify this. Let's call it, yes. So this pop is going to be for the word again. Yeah, so it's going to be for the people check. We call this 16, and then we close this, and then we rerun this to see what we get. Now, basically, we've seen how this works. Like, we've literally seen how to build a Bevy game with the understanding of it, the results that we expect to see, and all of those things. And if you do this, you can see that yes, there is nothing, but you can notice this weirdness in the sense that the cursor position and the viewport position actually are in the same place. So, but the word position and the word check actually maintains with the cursor. Why? Because we are using it with the camera. You notice what is happening here. It's working with respect. So let me show you what I mean here. If I move the camera, let me move this down a bit. How do you move the camera again? You can see it is scaling with the camera. Obviously, all of them scales with the camera, right? But that particular one, how do we move the camera again? WSD, no. We use IKL, no. Let's see. What's the way to move the camera again? What am I looking for? It's literally here. Oh gosh. Arrow keys to move the camera. Now you can see that as we're moving the camera, the viewports are moving with respect to that. So if I put it close to the top of this place, even if I move the camera, it's still aligned with the camera. So that means the viewports and now you can see that I've successfully been able to bring them closer. See the weirdness. So this is the weirdness of how camera works. So it's something you really need to like master and understand, but for now this works. And then if you need to make any adjustment that feels will take time, you can always leverage AI to make to save us time, right? So now we understand why this is coming at this time because it is actually aligned with this. Moving out of the window already takes it out. But the moment I'm this value in the window itself, the down value, nope, the 0 by 0 value. It stays at the 0 by 0 value of the camera also, just like this. And so that's what this the cursor position and what's the other one? Viewport check does. Right. So now you can see that we can make modifications to it. We can add more things instead of circle. There are other options we can do instead of circle. We can have arc, we can have arc 3D, we can have crosses, we can have cuboid, we can have ellipses, grid, ray, and others. So we can basically customize this to fit into what we want to do. Now I know that this may seem like a lot, but it's actually not a lot if you consider the fact that you can build this as much as possible. Isn't just this low code, 170 lines of code that defines what we need to do. And that's basically it. So this is where I'm going to wrap up this for today. I'm going to create a part 2 of this because this is just the part 1 series for this Rust and Bevy game engine. Maybe we are going to be building. We're going to be building more stuffs. There are a lot more examples. You can also try it out on your own to give you much more confident feel about handling it. You can read through the code, right? Because most of the things we're going to be doing is checking through the code, modifying them, tweaking it to become what we want. Like you can see, what we did was just the viewport to world. We still have all that complex stuff like the 3D, the 2D shapes, bloom post processing in 2D, mesh alpha mode. Let's know before we even get to 3Ds. Like these are things we can do in 2Ds. Sprite sheet, renders and animated sprite. So we can even start rendering in let's say in the next 3 videos if you are fast enough. And then transparency, then we go to 3D rendering where we have a 3D scene and all of those things. Imagine being able to make your 3D scene in just few lines of code. That's basically what Bevy can allow you to do. And you can do that with Rust. You just few lines of code also by understanding what you want to do. So you can try to create stuff like this, stuff like the atmospheric 3D blooms. You can create a camera with sub view, right? Where you know the camera, floor grading, all of those things. If you are very much interested in game development, this is more like a gift for you to start with. You can use it to familiarize yourself with game higher project. It should still be the same sort of stuffs, but not too different. But you can always use it as a starting point. So that's one of the reasons why Bevy is like cool for this kind of thing. And for the fact that it's written in Rust, it just makes it make sense. So there are a lot more examples you can check. You can create, demonstrating recasting, load and an actual model to a scene. Look, you implement light maps. And this is a yeah, these are 3D renderings, but implement light maps, generate custom mesh. Literally. So we're going to be talking about what all of these things. What is a mesh? What is we saw it on the other one too, where we have mesh 2D, mesh 2D. Something similar too. So we have and we can create lighting, create fogs, all of those. Then many more things that we can create too without understanding. So yes, that's basically all on Bevy for introduction purposes. And before we jump into more advanced things like creating this complex renders, or let me say UI, right? Because they are all user interfaces. Everything we create here, you can see example of sprite animation, sprite sheet. You can see all of those things, right? And they make sense. The mesh 2D, you have to mesh 2D, you have mesh 3D. This mesh 3D was what we used to create a rectangle on the one we just created, right? So we have also the manual mesh 2D, right? Replace the custom mesh manually with mid-level render APIs. We have all of this, and then you can render your model, import your model, and render it. All of those things are possible now because now we know what to use to implement them. So for the first series, or let me say for the first series, which is today, and just to give an intro to what is possible and to make it beginner friendly so that we don't overwhelm ourselves on the first series. This is basically how it works. This is Bevy for you. This is what we can create with Bevy. From creating a simple hello world in Rust to converting it to a Bevy game by just adding Bevy to just one line, add Bevy to your dependency, and then you have access to create a UI that you even create a game out of it if you want to. It's actually powerful to be able to create something like that just with a single dependency. And that's basically what we've been able to do today. From there, just dependency in cargo.toml to creating, to understanding what ECS is, to understanding the ECS system. The ECS system in terms of entity components and what? The system, right? So we created the ECS. We understand the ECS philosophy of Bevy. We implemented it. We implemented the entity, we implemented the components, and we defined what they are. We explained what they are. We understand how to derive them. We understand how to use them for definitions. We understand how to implement plugins and to create our custom plugins, which we've used. And by this, we already understood some basic, or let me not say, yeah, basic Rust concept and even some major Rust concept like struct, like public struct in terms of importing different plugins from and different modules, then implementing a struct on its own, those functions, passing parameters to the functions, mutable parameters or immutable parameters for read and write access, how to create different systems, how to convert from a system to a plugin so that for encapsulation or grouping, all of those things, it just makes a lot more sense. And we've learned things within space of 3 hours, right? We've learned how to, within space of 2 hours, we've created a sample, learned how to write Rust, learned how to write a basic Rust program, convert the basic Rust program to a gaming program that gives you UI, right? Using a render engine, and from there we can create a 3D mode, a 3D world. We can program it to have functions. We can program it to do stuff. We can then use AI to leverage to do much more powerful stuff if we want to. Now these are possibilities. I'm just opening our eyes to what we can create in this series. So basically, I understand that this is where we started from. And if you guys don't have any comments for all of you watching right now, then I can call it a date now. But same time tomorrow by 4 p.m. West African time, I'm going to be creating a part 2 of this series. I'm going to create like a schedule so you guys can get notifications. So please, if you're not subscribed, please subscribe to this so that, and turn on your notifications so that you can be aware and available for when the video drops. But I'll schedule the live session way before it starts, like maybe give you a 8 hours to 4 hours notice. Even from now, I can even create it now so that you are notified. But you can't be notified if you don't subscribe. So please subscribe to it, to this channel, and turn on the notification so that you can be aware for live videos, because there are a lot of things we are about to build in this series. So yes, enough of talking and talking and talking. So that's basically what I'm trying to do here. And yes, basically that's it. So we are building, from what we've seen here. It may not look like a game, but yeah, this is because you can see the, this is not a 3D game. You can call it a 2D game. You can create a game using this just by moving different things. Maybe moving rectangles, right? Increasing the rectangle length whenever we take it. Those are possibilities we can create by creating a game. So these are things we can do, and these are things we are going to do in this series. So yes, that'll be the end of the first part of this series. I know it took a while, but then we needed to understand the basics so that by the time we are going into this tomorrow, we are going to be making and diving into a much more advanced concept than what we've done today. And yeah, if you guys have any questions, please just let me know so that we can tackle that. Drop a comment, you can drop your questions. If you have any requests before we do this in the next 24 hours, literally, or let me say in the next 20 hours, then you can drop a comment and then I'll reply and we can move from there. But basically, this is it. This is Bevy. Not that crazy to create it now or using Rust now is that, and just a few steps. So yes, thank you all for joining this series. And if you're interested in Rust more, you can always drop a comment and I can always reply to you. I will always reply to the comments if you drop a comment on what you want to learn, and then we tackle it. We move from here. We are going to be learning by building. So we can build complex stuffs. And that is it for today's class. Thank you so much, guys, for watching. And get subscribed so you can get access to the new videos that will be coming up tomorrow and every day from now to the end of this month, basically. So hope so that you don't miss out on any of them. Yeah. Thank you so much for watching. Catch you guys in the next one. Bye for now. Peace.